You good? I'm not going to be able to. Give me just 1 minute, please.
Your slides are up there. You go to the top. So SNIA believes in both open standards as well as open source, and we complement those by having a technical work group in the SNIA be allowed to have both items in their charter, right? They can have what we call a SNIA architecture, which is a standard. We usually take those on to ISO or JTC1. But we also have projects out there in GitHub that are open source as well. Typically, those open source projects are going to implement some aspect of the standards, such as a reference implementation or perhaps test clients as well. And so we do feel that both open standards and open source are very complementary and do need to be worked together. Our current project in open source is the CDMI reference implementation. CDMI stands for the Cloud Data Management Interface, which has been an ISO standard now since 2012. We just published a new version of that, so that'll be a 2016 version of the ISO standard. And our CDMI reference implementation has an open source repository on GitHub that anybody can access. And also now, because of our contributors license agreement project, they can also contribute to the CDMI reference implementation as well. And because of its importance of standards development as well, that means the adoption is not just a matter of picking up code and using it everywhere, but also allows independent implementations of the standards outside of the open source. Companies can develop proprietary information, proprietary code, as well as the open source adoption as well. Basic bottom line is that customers get what they need. They need the freedom to choose from multiple best-of-breed implementations.
That sounds like fun.
I can do air guitar flamenco. Good morning. So hope everybody had a great week so far. Doesn't feel like Wednesday to me. So welcome to SDC, and we got an exciting lineup this morning. Just some brief remarks about SNIA if you haven't heard of us. We do all this stuff: standards, PlugFest, technology information initiatives, education, events, and open source. Thanks to all our sponsors. We couldn't do this without the sponsors' help. And to help us encourage these sponsors to sponsor again next year, please visit their booths and chat them up and find out whether what they have is something that you need. So this morning we're going to have a panel, and then we'll have 3 keynote talks, and then in the lunch and sponsor showcase, we'll be out where it was yesterday in the mezzanine. So while you're eating lunch, go around and visit those booths. We have breakout sessions this afternoon. We have a single BOF slot at 5 o'clock just to keep you around and away from the traffic. And then a special anniversary event this evening from 6 o'clock to 8, and there'll be some interesting things happening. I don't want to give it all away. We do have a mobile app, and there's plenty of reasons to download the app, but one of the things we're going to be doing with the app even during this morning's session, is you'll see a little notification that comes up, and we're doing a survey of the developers that are here at the conference, things like programming language that you like, what do you work on, so you can see sort of what the other developers around you are into. And so watch for that pop-up app and take the survey, please. So if you're into social media, please tweet about us. Hashtag SDC17. There's a lot of tweets already with SDC17. We're trying to keep an eye out for them and retweet them whenever we can. And then we have a SMB3 Plug Fest downstairs, doing some great work around interoperability and the SMB standard. We have a Cloud Interoperability Plug Fest, and we have Storage Management SMI and Swordfish Plug Fest. So we'll have a panel to start things off, a little, interactive. We'd like some questions from you for the panel. If we don't get those, we got some questions lined up just in case. And then we're going to have Stephen Bates come up and talk about Linux optimizations for low latency block devices. Stephen's always a great speaker and interesting and informative. And then we'll have Carol Wilder from Intel give the Data Intelligent Storage keynote. And then we'll find out about persistent memory, new tier or storage replacement from Kimberly Keaton. And then the BOFs this evening, there's a couple BOFs, open source and SNIA BOF, and comparing iSCSI, ISER, and Nvme over Fabrics. And then the celebration. The evaluations have gone out. You should probably seen them in your email or in the app. Sometimes they come up in there. I think you can get a link to it. But we do have 2 $100 gift card winners already, and we'll announce those right before you leave for lunch. So if you want the $100, you got to get your evaluations in. So have a great SDC. All right, can we get our panel members to come up here? So our panel is on the impact of persistent memory on SSDs and fabrics. So persistent memory is disrupting storage architectures. The low latency persistence impacts software devices and networking. The panel will focus on the impact of solid-state devices and fabrics. Nvme over fabrics is just now emerging on the scene. Will it be capable of persistent memory over fabrics? What do SSD controllers require for the lower latencies and new channel speeds? How will the management of security be handled? So we're going to have brief presentations by each of the panelists, and then we'll do the Q&A for the rest of the session. So, Everspin, you're first. So Terry Hewlett, Vice President, Systems Engineering and Systems Solutions Group, Everspin, is a VP of System Solutions at Everspin Technologies, where expands Everspin's capabilities and business strategy as a world-class solution provider.
Thank you, Rick.
Mark.
Mark, sorry.
So
Thank you, Mark.
This is to the right to go down.
Okay. Hi, good morning. It's not that early, so it should be okay. At least I made it, so a lot of you did. I appreciate that. So as Mark said, my name's Terry Hewlett. I run a group at Everspin by the name of System Solutions, and most of you probably know something about Everspin at this point. We're the MRAM guys, and we've been delivering MRAM to the marketplace for a long time, and you don't want me to sit here and tell you a bunch about MRAM. But I can't help pointing out a couple simple facts, right? We think of memory. Okay, and that's got write characteristics, and DRAM and SRAM have been our constant model for memory for a long time. And the write characteristics are such that you can write it very quickly, and you can write it many, essentially infinite times. The CMOS wears out first. So we have things we consider storage, and I think NAND is going to be the lowest cost per bit for the next 10 years. So it's a solid-state storage device. But its write characteristics are the other end of the spectrum from things we think of as memory. Well, there's an MRAM technology that we have that actually falls in the category of memory and from its capabilities. It's got the endurance and the write performance that's close to, but not quite equivalent to the DRAM and SRAM technologies, but it looks like memory. The other things we call storage class memories are very, very good read buffers. They have a good cost per bit. It's not quite NAND yet, but hopefully they'll get there someday. And their read characteristics are much better than NAND. However, their write characteristics are only a little bit better than NAND, which means that the MRAM technology that we have is useful, even though its density is much slower than the other technologies. It really comes into play as a write buffer for things going to lower cost per bit storage. So that's the basic positioning of MRAM technology, and I'm going to move on because this is not about a chip technology session. No, too many builds. So what we did was we actually took the MRAM technology and we made some SSDs out of it. The storage is all MRAM, and the capacity is tiny. And we were talking about megabit and gigabit chips today, so we have gigabyte type storage devices, but the performance characteristics are crazy. We're actually seeing less than 6 microseconds for 4K random writes from a standard NVMe driver. You use SPDK, we're down to below 3 microseconds for 512-byte writes. So its performance characteristics are radically different than things you normally think of as an SSD. When you add those characteristics into an SSD, now you can actually make SSDs out of lower cost per bit technology that fundamentally will give much better performance characteristics. But I want to show you a couple things that we've done with this device so we can really start to think about where persistent memory plays in the storage fabric. Okay? So if it hadn't been called the Fire Memory Summit, then there would have been a presentation where we were doing, we were actually showing how MRAM technology on a PCI card, and so it's an NVMe device that also has a memory mapped I/O capability. So it's byte mode addressable as well as block mode addressable. And so we were actually doing 64-byte messages from a client machine through a 40 gigabit per second network into memory on our card on the other machine. So there's actually the data is not going into system memory. It was actually going reads and writes into memory on the NV Nitro card. And that demo was going to be doing 2 microseconds to persistent memory on a remote device and 10 million messages per second. So now you can start thinking about, I can do remote logging. I can do remote messages, into persistence and, extremely low latency times. From a bandwidth perspective, it was still pretty good too. This turned out this demo was limited by the 40 gigabit network that we had to connect the two together. So what we decided to do next was, well, let's upgrade to a 100 gigabit network and upgrade to a later card from our friends at Mellanox. And it's, so we're actually doing NVMe over fabrics to our device now. And out there, it's running at 19 microseconds for remote persistent storage at about 1.4 million 4K messages per second. And it'll sit there and do it all day long. That's pretty cool. Now you can actually have remote storage in less than 20 microseconds. What's going to be more cool, though, because our friend Oren at Mellanox was explaining to us day before yesterday now, wasn't it? That using the persistent memory on the card as the place to put the submission queues and completion queues and data in flight, then we can do a complete offload from the host machine. There'll be no CPU utilization on the remote machine and no memory utilization on the remote machine. And we believe at that point the storage will be below 10 microseconds for 4K random writes to remote persistence with actually no load on the host. This opens up all kinds of opportunities. We've always, I was an RDMA guy for years, and we've been trying to figure out how to build scale-out environments where you can actually share memory first with RDMA, now storage with NVMe over fabrics, and the capabilities there, especially once you get persistent memory on PCI, really open up for you guys to do a lot more thinking. I'm a hardware guy. In fact, I'm a component level hardware guy, not even a system level hardware guy. And I know SNIA is mostly about, you know, delivering great storage software ecosystem. And I think that's hugely valuable. But we need you guys to think about what this kind of technology can be used for and how we should use it. I don't think the standards are done yet on how we talk to persistent memory on PCI. I think there's a lot of value in expanding that, and we just want to be a part of it. So, thank you.
Okay.
To go to the next one, thank you.
All right, thanks, Terry. Our next speaker is Rick Kumar, Vice President of Product Development, New ISIS. Rick is the Vice President of Product Development, a provider of advanced data center products. Prior to New ISIS, Rick worked at Oracle for more than 15 years, serving in numerous project and engineering management, overseeing large global teams. Please welcome Rick.
Morning, everyone. I'll be talking about NVMe over Fabric and some of the things we need to consider as an industry as we implement Fabric in real-world environments. As you look at what's happening in the world, the latency continues to go down, but along with latency comes some of the management headaches that we as an industry have to consider. We've been working with our partners and with our customers to look at disaggregated storage and how disaggregated storage with NVMe over Fabrics can be implemented. Obviously, latency has been a big driver of this force. With the efficiencies that it can deliver, we need to look at some of the management aspects of how we would implement it in large-scale deployment, particularly with cloud service providers that are managing hundreds and thousands of nodes at any given point. Disaggregation also brings efficiencies from both scale up and scale out perspective. So there are many, many benefits on how we would go about doing this. So management at scale, particularly for hyperscale customers, the feedback we've been getting and what the industry has been driving towards is how do we manage something out of band? Everything we talk about has been in-band management, but out-of-band management for security reasons have become quite relevant for our customer bases. So we're looking and working with our partners to deploy some of the RESTful-based APIs that would support open standards like Swordfish. And these things will enable customers to manage the enclosure health, the security, i.e. access to the storage itself, error monitoring, and firmware management, which we all have to deal with as time goes on. I'm going to be showing a couple of examples of some of the applications we're looking at deploying. The first one is a Cassandra implementation that we're working on with, again, customers in the industry. So Cassandra, multiple customers are using that out there. What we could look at is NVMe over Fabric with multiple copies of the same data set across the network. With the host connected to it, some of the testing we have done has shown 50 microsecond latency on NVMe, standard NVMe, and certainly there are other technologies coming to market that will drive that number down. If you were to lose one of the storage nodes or one of the hosts, how do you manage failing over to another node or a host? And that's where the Fabric Manager comes in. We've been working on trying to implement something that does that centrally, such that you can manage the security, you can automate the storage features that you need at the data center level, and perform and do continuous monitoring of the health of the network, the errors, and anything else that the customer may need. And it allows us to fairly seamlessly fail over to another node with minimal disruption to the customer. This is an example of how one could go around implementing spectrum scale or GPFS in the industry. So this is, again, another node that's connected to a number of GPFS clients, servers, which are then connected to a number of clients. we've been able to demonstrate running RAID, so data protection across NVMe over Fabric, and yet deliver with a full file system loaded on sub 90-second microsecond on the latency. Now, that did use Optane drive, so it was extremely efficient in that perspective. So these are just examples of how our node and the clients can grow in a data center very easily. And what we're advocating is driving a out-of-band management interface that complies with standards that are already out there. Thank you.
All right, thanks, Rick. And our last panelist is Dr. Andrei Vityev, Chief Strategy Officer for Mobivil. Andrei is the Chief Strategy Officer at Mobivil, a Silicon IP and platform developer for storage and IoT. He is responsible for new business development initiatives at Mobivil. He has served as a founder and CEO of Proton Digital, an LSI fellow, and worked with numerous Silicon Valley companies. Please welcome Dr. Andrei Vityev.
Hello. So I will talk about latency and throughput and SSD controllers for persistent memories. To introduce Mobivil, we are a Silicon IP and platform provider. We focus primarily on storage, but we also have products in networking and IoT. In storage in particular, we have this SSD controller platform that you see shown on the right, where we have various blocks that we license to customers, as well as in some customer cases, we also provide them a complete platform. So you see all the standard blocks within the controller, PCI Express, and Nvme controller at the center of it, flash reliability, /LDPC, flash sequencer for talking to flash, and so on. What is interesting is that we have to work with a wide range of customers. These customers have a wide range of requirements on the data rate and on the latencies in particular. So as a result of our business model, we are forced to stretch our blocks to a higher degree than perhaps what designers have to do at classical semiconductor IC suppliers for the controllers, because we face a wide range of situations. So as a result of that, it was necessary for us to create a high degree of scalability and configurability in this SSD controller platform. At the most basic level, the data path widths of every blocks shown in this diagram is scalable and configurable. So as a result of this scalability, we are deploying this controller platform to persistent memories. So the platform originally was designed for classical flash memory, and is deployed in the persistent memory case. We did a press release yesterday announcing a partnership with Crossbar, where Crossbar and Mobivil are applying this controller platform to develop a resistive RAM SSD and resistive RAM NVDIMM. So on this slide, courtesy of Crossbar, we're showing the performance specs of the resistive RAM SSD that is under development. Note that the performance numbers shown here are based on measurements of the existing components that will make up this SSD. For Crossbar, of course, resistive RAM has already been demonstrated at a previous conference. The latency of the memory itself in this sort of a large capacity configuration is 1 microsecond for the read and 2 microseconds for the program. There is no erase required, makes garbage collection a lot easier. For the controller, controller is a deployment of the Mobivil platform controller that is configured for this specific application with its latency and throughput requirements, together with necessary customization and addition of some other components. So as a result, you get this NVMe module shown here on the right. Let's see if I can point this. Not quite. So on the read side, the latency is 10 microseconds in the worst case. The random I/O performance is 6.4 million random I/Os at the 512-byte block page boundary. So the page size obviously doesn't need to be as big as it is in case of flash. When you're working with 4KB blocks, the numbers change, but the overall throughput is the same, 3.2 gigabyte per second. On the right side, the write performance is 10 microseconds without caching, and this is the worst case, 10 microseconds. The same random I/O performance, 6.4 million random I/O per second at 512-byte blocks. There is no erase prior to write required. As I mentioned, that eliminates garbage collection. Endurance is not unlimited. Actually, in this specific configuration, it's 100,000 write cycles. Crossbar itself has demonstrated at a previous conference 1 million cycles. They did a demo in the conference itself. But for the product itself, 100,000 cycles are specified. There are several technologies that allows Mobile to achieve this design specs. First is a scalable design. I mentioned that at the very basic level, the data path widths within the blocks are configurable, and there are other programmable and configurable parameters as well. The other one is that FTL is implemented in hardware. All the page level operations are done entirely in hardware with the corresponding address lookup and everything else. In case of a flash version of the same platform, the block level operations are handled by firmware, such as erase or figuring out which blocks to allocate for writing into, but the page level operations are done entirely in hardware. And this is the same implementation. Here, obviously, it's the same platform, and this is what allows us to achieve this performance specs. In general, we try to do control blocks by having programmable state machines and by having sequencers, instead of trying to insert various small microprocessor cores. So we found this design to be simply more scalable across different customer configurations. And we also found this design to be more reliable in terms of having lesser probability of a design error of some sort. So again, this shows an example of not sort of an ideal design when somebody gives you $300 million and tells you, go ahead and build the very best possible clean sheet design. This shows sort of a very practical solution, taking a platform that was designed originally for the flash implementation, but that has sufficient degree of scalability and flexibility that it can scale to this design and achieve this performance specs. So in case of the Nvme version of the design, this is much more parallel design. There are more channels here. There are 16 channels talking to, I cannot point this. There are 16 channels talking to resistive RAM chips, DDR3 64-bit wide interface. Latency drops for read case from 10 microsecond to 4 microsecond worst case. The random I/O performance is 24 million random I/Os at 512-byte page boundary. Obviously, the numbers scale when you use 4KB blocks. Write latency also drops from 10 microsecond to 4 microsecond. This is without caching. And the same spec for the write cycles as well. So again, as I mentioned, all these numbers come from measurement of the existing blocks, measurements of the blocks that come from the Mobile controller platform, as well as measurement of the resistive RAM samples, which are already available. Lastly, I want to touch on a completely different topic, sort of going back to the controller design in general. This is separate from crossbar implementation. Latency and error correction coding. ECC is a necessary element in every memory. It allows you to bring technology to market sooner. If your manufacturing process is not perfect and you're facing some errors, and when you're trying to read the data back, you can correct these errors with error correction coding. So as long as you have sufficiently low latency and high throughput and good implementation, it allows you to do more with the existing manufacturing technology. So the question is, what is the latency? There is a wide range of latencies which depend on the type of error correction code being used and the code word size and how many bits you're trying to correct. Because there are different types of ACC code, some of them based on algebraic decoding, some of them are based on probabilistic type decoding. So it's a pretty wide range of latencies and throughputs as well. When you're trying to correct only 1 or 2 bits per small code word, latency can be minimum. You can bring it down literally to just 1 or 2 clock cycles in the best case scenario. And then if you're trying to correct more bits, then you have to increase the latency. So we wanted to see what is the latency for the most powerful case. The most powerful ECC which is available, LDPC stands for low density Parity-Check, can still have low latency. So as part of our controller platform, we have LDPC compiler that's been deployed in a few customers in production and all. So we run that software to generate RTL for a configuration that we think would have fairly low latency, and here are the numbers. So beginning of life, when this code has to correct few errors, not 0, but few errors, is 75 clock cycles. At the end of life, when you're getting close to full capability of what the code can do, you get into 155 clock cycles. The design has quite a bit of margin in it. So with the high density, with the high speed library, you can basically, this means 155 nanosecond latency at the end of life. But again, this design was really optimized for size of implementation. It wasn't actually optimized for latency. And the question is, can we do better? And the answer is yes, absolutely. We try to go through a process of figuring out what is the theoretically best case latency for LDPC, going through the algorithm, what it does, and looking at the sequence of calculations you have to do and what it would mean in digital implementation. And we get in numbers of 12 to 15 clock cycles at the end of life. So certainly something less than 20 nanosecond with the implementation that's geared towards lowest latency instead of smallest size. Okay. So in summary, this is what mobile were able to do with this controller design that was scaled to a persistent memory application.
All right, so these guys are not just up here talking. They actually brought their stuff and are demoing it out here in the mezzanine area. So if you look for Everspin, they have an MRAM enabling low latency Nvme over fabric applications. Nvme over fabrics with all the standard drivers achieving surprising latency. And then we have from Mobile an FPGA-based SSD platform that incorporates PCI Express, NVMe Express, LDPC, ONFI, and DDR4 controllers. The platform includes FPGA board, FMC card, flash SODIMM, and hardware-based flash translation layer. An appliance from Nvme is demonstrated that can be deployed today and supported disaggregated storage with best-in-class latency. Management software supports RESTful API that can be used for storage administration in a similar fashion to today's storage. And I believe there's also a Samsung demo out there as well, right, Bill? Yeah. So go check that out and ask questions. Speaking of questions, we'd like to hear from you. What do you think the impact of persistent memory will be on SSDs? What new standards might we need to do? And again, a reminder, we are streaming this live on the internet, so if you could, raise your hand, wait for Marty's microphone, and then ask your question of the panel. Just raise your hand, like this.
SW, you left.
Yeah, give him the mic anyway. All right, well, to get things started and so on, why don't we have a question for Terry? How would you use such a small storage capacity? You're talking a gigabyte drive, right?
Yeah, and that certainly is a question we get often, right? I mean, the MRAM technology is extremely fast, and the endurance is amazing. We're talking billions of cycles, not hundreds of thousands of cycles with technology. But then what do you do with it? So the first and most prevalent use case is a write buffer to other devices. Okay, so you could take an all-flash array, you could put one of our devices in, it could be the write buffer for everything else, and use cheaper consumer-grade NAND for the storage and the other slots. There's also a bunch of interesting cases inside of an SSD itself, and it's still the same write buffering thing, but the big challenge with managing NAND today was already mentioned here, is garbage collection. And the fundamental issues around garbage collection are getting worse and worse every day because the NAND block size is growing. The common storage block size is 4K bytes. Many applications use 512 bytes. But the NAND block size is in megabytes and growing. So what happens is you end up with data stored in a NAND block that's from totally random threads, and now the garbage collection problem is amazingly challenged, right?
And a bit of noisy neighbor as well.
Yeah. So if you can actually buffer enough data in flight to locate data in the NAND blocks that has some logical association with each other, now in some cases you've wiped out the garbage collection problem because it was all one file, you invalidated.
Sounds like streams.
Rates, right? But that takes an amount of buffering that's really not achievable in a U.2 form factor with supercaps and DRAM. So
okay.
MRAM's a great use case for that.
Rick, Andre, you want to address the question? No? Okay. Hey, we have a hand raised. Go ahead.
Thank you. I just have a follow-on question there. In terms of MRAM, what is limiting the geometry scaling? Is it scaling, and where do you see it go in terms of cost over time compared to the DRAM as well as 3-dimensional?
Yeah, so MRAM, the products we're shipping today are made from a standard CMOS foundry-based logic process from Global Foundries of 40 nanometers, okay? Our 1 gigabit chip, which would have been on display at Fire Memory Summit, was made a standard 28 nanometer technology. The scaling of the MRAM bit really comes down to the diameter of the magnetic tunnel junction, and we're scaling it down every 2 years. I joined Everspin 4 years ago, and not because of me, but during my time there. We've dropped the cost per bit 16x, and we don't see that changing for another, that trend line should stay for another 4, 5, 10 years, okay? There will be a day, we believe, where an MRAM bit is a smaller area than a DRAM bit, and then it really comes down to manufacturing scale.
Thanks, Jay.
Any other questions? All right. Rick, what are the benefits of disaggregation?
All right. So with direct attached storage, you're always forced to plan for worst case scenario. And with disaggregated storage, you can dynamically allocate storage to applications, to servers, and as the need changes, you can optimize your utilization of the assets that you have in your system and your environment.
Anybody else want to address that? No?
I mean, disaggregation is fundamentally, data centers used to be built with, every machine being the same and there being a million machines there. And what data center managers found out was that they're wasting a lot of compute resources, or a lot of storage resources, or a lot of memory resources, because every machine had to be configured to run the large job. with disaggregation of storage and other technologies, what we find is that data centers can be much more efficiently scaled, and it's great. I mean, we need more of it.
So we're moving away from direct attached storage, even though we were just moving towards direct attached storage.
It's a perpetual cycle, isn't it?
The use cases are so broad and the market's so big today, nothing is going to die in the near. I mean, hey, look, tape drives are still heavily used, right? Okay,
right.
So
that's really disaggregated. Any other questions? Come on, guys. Yeah, this is interesting stuff. All right, back to Terry. How do you compare to Optane?
Another common question for us. The graph showed it. From a read characteristic perspective, all of the resistive memories, 3D crosspoint, phase change, conductive bridge, resistive RAM, they all have good read characteristics. I mean, no one's right on top of DRAM, and MRAM's in that category. We're not 100% of the DRAM kind of performance, but very close, within 2, 3, 4x in terms of the DRAM characteristics. That's not where the difference lies. I mean, I think 3D crosspoint is going to be an awesome technology if and when they can get it on the memory channel and pull a bunch of storage into an area where that you can access it very quickly for large-scale databases. What MRAM does, though, is it provides persistence for the writes that the other technologies can't do, right? So I don't consider the other storage class memories as competitors to MRAM. I think MRAM makes them all better because it can soak up the writes and then distribute it in the back-end storage in a way that the other technologies can deal with it. And that there's not going to be one memory that's the whole world in the future, right? Just like I mentioned tape drives, we're studying tape drives. It's how you tier the storage hierarchy and how you use the different technologies to provide the benefits that our customers need.
Yeah, well, NAND SSD started out very expensive per bit, and you would just put a little tiny drive in there to accelerate the rest of the stuff, right? So this is a new sort of acceleration kind of storage tier, right?
Yeah, and who knows where this storage tier ends up, and maybe it actually ends up on the CPU die because the technology is highly integratable with standard logic technologies. So there will be a day where all memory except for the register files inside the CPU is persistent. Right. Maybe L1
we'll
is
swing
still
back
not
to DAS
persistent,
again. Other questions? All right, keep going. Rick, what management capabilities are needed to deploy at scale?
Right, so today, some of the standards that are available does management in band. As you grow the number of clients, as the number of users grow, would you want to trust your allocation of storage to the clients themselves? So what we've been discussing is creating an out-of-band management capability where your namespaces, your storage resources are allocated to specific clients and can be failed over or can be persistent across multiple environments. So you scale your disaggregated storage, but you also need to be able to manage who you give storage to and what storage is available.
What about Swordfish?
Obviously, want to integrate with that.
So he's going downstairs after this to participate in the Plug Fest.
There's a question that's coming in on the internet.
Online, yes.
So,
questions are available
I
from
think
the
it's
internet.
a question for Andre, wanting to expand a little bit on the impact or the meaning of security in a persistent memory system. Maybe expand on that topic a little bit.
Well, I think the issue is you want to maintain low latency in case of security computations as well. Security computations naturally, involve obviously a fair amount of mathematics, but I don't think that the latency challenges in securities would be at the forefront of the latency challenges for the controller itself.
But doesn't security impact your latency? As you're
it
encrypting
does.
And decrypting, right? That isn't true.
It does, but also the question is how do you implement security? there's very interesting sort of branch of mathematics involved in security with the number theory and all. And it's the same sort of subject matter as in the low-density parity-check codes that I mentioned. You can have a design optimized for silicon area, and you can have design optimized for latency. Mathematical formulas change. I'm sorry, mathematical formulas stay the same, but the implementation is different. So at this point, in terms of the challenges that we had to deal with, obviously trying to port FTL, most of FTL implementation into hardware, this required some work, especially because you're taking some algorithms and firmware that you can easily modify if you have an error into hardware where you have to guarantee reliability. So FTL challenges, required some amount of work. Some of the other blocks required amount of work. Security hasn't. We don't see it as a challenge in terms of latency. I'll put it this way.
Well, but what about when you're disaggregating and you now have your bits on the wire? They leave the box. Is that secure?
I think for that question, we probably have to bring some of the other people from Mobile to answer.
Anybody else want to address that? Rick?
We've seen different models being implemented for security. Some of our customers are actually going out and securing the data or encrypting the data even before it gets into the network. So what you end up receiving on the storage node ends up being encrypted to begin with. So from a latency point of view, you're not doing any compute, you're not doing any additional work at the storage level.
All right,
you're receiving the data already.
Just like the cloud, encrypt it before you get it there.
Right.
Okay. Yeah. You need a mic. Wait.
I don't need a mic.
Yeah, the people on the internet do. You're not that loud.
So talking about on the security side, I mean, we see some of the new processors offering inline encryption engines for the memory channels, right? So the AMD processor, and we're just putting the Linux drivers in for that now for key management and saying, I want this part of memory to be encrypted on the way to the DIMM or the NVDIMM or whatever. So are you guys able to leverage some of that where it can do the encryption of the data going to those kind of devices? Is that something that you guys have thought about at all, tying into that new hardware that's coming?
So it depends on the implementation and what the architecture is. From a disaggregated perspective, it doesn't really play into that aspect of things, but certainly if you had direct attached storage, you have to implement security at somewhere. And that could be done at CPU complex level or some other layer where the data is actually coming in secured. And if it's not secured, then you will consume compute cycles to make that happen.
Okay.
I'd say certainly in our implementation of NV Nitro, if encryption on the fly was desired, the FPGA has plenty of space to add that in.
Another question? Okay, let's see if we have any. Oh, yeah. Back to Terry. Since NVDIMMs are mostly enabled now, why is persistent memory on PCIe interesting?
Well, I could give you my answer, but the gentleman at the back of the room will give you a much better one sometime today or tomorrow.
Next.
In 8 minutes. So, the compute cycles are there for running applications, and what we need to do is deal with storage in the fabric.
Right.
Okay, and persistent memory in the fabric provides a buffer, a way to handle the queues, all kinds of things that you need to deal with at the memory level instead of the block level, and do it in a distributed way in the fabric, and keep that workload off the CPUs, the main CPUs, so that they can run the applications the customers desire. And like I said, Stephen knows far more about this than I do.
We can't hear you, Stephen.
Thursday? Is that Thursday? Okay.
Okay, no more questions from the audience. Rick, what performance can be expected with disaggregation?
So we've been doing different workloads. In certain cases where you're doing pure export of NVMe, we've seen latency as low as 40 to 50 microseconds. Certainly, again, with different technologies coming into the market, you can further reduce that. With file systems, again, we have been testing different file systems. GPFS, we were getting down to under 100 microseconds. Again, these are all ideal conditions where there is not a lot of network congestion, so network plays into this, and that's something, again, we're working with customers to figure out how to architect that in their environment. But from a pure execution perspective, 100 gig network going to 100 gig network, we're seeing very, very competitive latency and disaggregated storage.
But what are you comparing that? Are you comparing that to DAS? Because
no,
as soon as you remote it, you're going to suffer performance, right?
You will.
Yeah.
Yes.
So, okay. And if there's no more questions from the audience, no? Okay. We want to thank our panel. All right, our next speaker needs no introduction. Stephen Bates, the Chief Consultant at Ratlin. He works extensively on storage architecture, non-volatile and persistent memory, and the intersection between performance barriers, performance hardware, and performance software. He has been involved in the architecture and development of both RAID-based and flash controllers. He has intimate knowledge of the most common networking and storage protocols, including NVMe Express, SAS, SATA, PCI, Ethernet, and RDMA. He has worked on a variety of CPU architectures and is active in the development of the Linux kernel. Please welcome Stephen Bates.
Hi, everybody. Hello, everybody. Sure, I'll try and use this. It's on. I don't know about singing in this one. We'll see. No singing. No singing? Just for you. La la. There we go. So my name isn't actually Stephen Bates. I'm Adan Burstein from Mellanox. You can tell by the braces. Believe it or not, I lost a bet in a bar last night, and I have to wear these. They are actually Adan's braces. I kid you not. So thanks a lot for coming, everyone. I'm going to talk about the things that some people have been doing in the Linux kernel to support low latency block devices. And I'm going to talk a little about low latency block devices and some performance data, and why this is a good thing for everybody, and kind of give you an update on what's going on there. The person with the time limits, where are you? Can you wave? Perfect. So last year, I was terrible. I ran overtime. Mark had to literally punch me to get me to stop talking. Yeah. So I want to make sure I don't take too long and we get a bit of time to have a chat about it. And I also want to start by saying thank you, Martin, for his excellent talk yesterday. If you missed it, you did miss out. It was a very good kind of broad overview of what's been going on at the block layer of the Linux kernel. If you missed it, I suggest you get the slides, and if it was video, maybe watch the video. Very, very good. Thank you, Martin, because it was a great introduction to this section. So, just as a reminder, I have this word called blucky. It's not my word. It's my son's word. He made it up. It's blah and yucky combined. So he uses that a lot. And I just want to start by saying, personally, I think low latency block devices are not blucky. And a couple of recent LinkedIn posts, I've been talking about some of this, and some people have been jumping back and saying we've got to go byte addressable. Other people are like, well, we're maybe not quite ready for byte addressability. I see persistent memory, which I'm a big fan of, and low latency block being very complementary to each other. They can work together. They can solve different problems, or they could solve the same problems. So I think we are definitely very excited around persistent memory and what its byte addressability capabilities can bring, but there are still challenges that have to be addressed. And in the interim, at the same time, we're getting some pretty interesting new types of NVMe devices. And NVMe is a block protocol with really low latency, and we'd like to be able to take advantage of those. And I'll talk about that through the talk. And you also got to see a picture of my kids. Really cute. Another reminder, what is a block device? In Linux, a block device is just a file, like any other file in the in your file space, in your namespace. So we have things like /dev, right? That's the device tree. And if you do an ls on a /dev, it will tell you, is it a character device, or is it a block device, or is it a directory to another level of devices? And if you do an ls minus l on a block device, it starts with a B, and that tells you it's a block device, and you know that you can talk to it using block device semantics. So I can open it, I can read it, I can write it, I can seek it, and do all those things. Now, what happens underneath depends on what the block device is backed by. And in the Linux kernel, we have all kinds of things. We've got crazy things. We have null blocks. So this is essentially a test block device that Jens wrote, and we use it all the time because it doesn't do anything. When I write to it, it says, I got your data. It does not have your data. It totally disregarded it. But it gives you a response. And when you read back, you get zeros. Or like me, I hacked it, and it gives me like Stephen Bates is awesome over and over again in every LBA. Right? You do that. It's great for testing, but it's not going to store any data, but it's good for testing. We have PMEM devices now. PMEMs are block devices, and there was a really good talk yesterday from Intel on DAX versus libm. We have a lot of different ways right now of talking to things like an Nvme or other types of persistent memory. But one of them is a block device mechanism where they've taken all those physical ranges of NVDIM memory and they've put a block kind of interface and software above it, and then they've presented that out as a block device. You can put file systems on it. If you don't put a DAX-enabled file system on it, that file system could go very, very badly wrong for you, but you can do it. And it might work until power loss occurs and bad things happen, right? So it's backed by persistent memory. We have the lovely, wonderful /dev/NVMe0N1. I love this one. Right? This is an NVMe device. It's an NVMe namespace. You might have multiple namespaces on the same device. You might have multiple devices. Those devices are typically NVMe solid-state drives. And today, they're typically backed by NAND. But I'm going to show you some examples that are not backed by NAND. So if they're backed by not NAND, then they're backed by AND, right? Boolean joke of the day. Okay. I like that joke. And of course, that device is talked to through the NVMe protocol. Interestingly, that NVMe protocol initially was only PCIe, right? Direct attach. But now that NVMe 0N1, that could be a Fabrics NVMe block device. And rather than talking to a local NVMe drive, I may be talking to Fiber Channel or RDMA and soon coming TCP/IP to go across a network to talk to a target that may or may not have NVMe drives in it. And that's the beauty of NVMe over Fabrics. That's the dirty secret of NVMe over Fabrics in the Linux driver, is you don't actually have to have a single real NVMe drive in NVMe over Fabrics. It could be a null. It is a null block device in most of my testing. It is because I can't afford to buy NVMe drives. Yeah, I have. Now I have. That's why I had to form a company to build my own, because I couldn't be bothered buying them. SDA1. So we have SCSI attached devices. These are more classical. This could be a SAS drive or a SCSI drive. It could, or a SATA drive. Sorry. It could be an SSD. It could be a spinning disk. We have network attached stuff, so we have network block device. And then in the Linux kernel, we have a layer called the device mapper, which allows us to take multiple block devices, which don't have to be the same. They could be a mix of some of the ones I've shown you above. And you can do interesting things with them. You can RAID them, so you can basically stripe data across them. And that, with hard drives, that sometimes got you better performance. You can do software-based RAID. So the MD layer basically takes a bunch of drives, reserve some of them for the error correction parity, and then using either an offload engine or just by doing the Reed-Solomon calculations with the instruction set, it generates the parity. You get your data, and you also get protection, and you can choose the level of protection. Now, maybe depending on your processor, not super performant, and you're probably giving up a lot of CPU cycles, but maybe you're using an offload engine, which is taking care of some of that for you. All right. And then applications can talk to these block devices, and there's standard ways for talking to them. We typically don't talk to them directly from an application layer. We typically put file systems on them because we like talking to files. But you can build your own file system, or you could be doing something. So you can certainly open a block device and read and write. At that point, you're reading and writing to specific LBA ranges rather than writing to files on a file system on a block device. But you could do it either way. Digging now into the physics or the physical thing of what is an NVMe device. I don't have a drive. I could have brought one with me so I could hold it up. But when you get down to real drives, the real drives that can actually store data, They typically have some form of attribute, right? So a block device typically can be randomly accessed. I'm able to go to a specific point. We tend to call those logical block addresses and say, can you give me the data from logical block address 941, please? And it will do that. It will say, I will give you a logical block. How big is a logical block? Well, I think pretty much any block device you can format, so you have some control over what that is, but typically the values that we see are things like 512 bytes, 1K, 4K, maybe 64K. So that's something that depends a little on the device and what you want to do with it, but you can't, at that drive level, say, I want 1 byte out of LBA 47, right? The drive doesn't know how to give you that. It can give you LBA 47, and the operating system can certainly chuck away the bits you don't want and give you the bits you do want, right? And that's what we use the page cache for quite a bit. But the drive itself has no way of giving you half of a sector. Operations have to be done on sectors. The other thing a block device typically gives you, which is one of the things that is challenging to us in the persistent memory world, is atomicity, which is if I do something, I do it either in its entirety or I don't do it at all. So if I do a write of LBA 47 and the power disappears halfway through or something goes wrong, I don't expect to have what's called a torn sector. I expect that 47 has the old value before the write started, or the other alternative is the write completes and the completion message is passed, and I know then the new data is on that block. Right? And POSIX has lots of rules around, if you want to be POSIX compliant, you have to follow certain rules on things like this, things like ordering and atomicity. And block devices try to do that. Persistent memory, because it's byte addressable, becomes much more challenging because you can now actually start to write half a sector and suddenly the power goes away, and so you get half of one sector, half the new data, half the old data, torn sector, very, very painful. The other thing is that a lot of block devices, not all of them, but certainly a lot of the block devices that I work with and care about has what's called a DMA engine, Direct Memory Access Engine. This is a piece of hardware on the drive that the driver ends up telling it what to do in terms of data movement. So with persistent memory, typically the way you get the data into and out of the persistent memory is using the load store instructions on the processor. Now, there's games that can be played there, but let's just assume that that's typically the way you would put data into something like an Nvme. The challenge with that is those loads and stores are being run on that expensive Xeon or ARM64 or whatever, and those instructions are consuming that core, so it can't do something else. You're basically spending a lot of money to buy a core to move data around. And I think at some point in the history of computing, we realized that's not a very good way of spending CPU cycles. So we thought, well, there's actually a better thing to do here. Why don't we get the CPU to talk to some cheap thing that's in the system and say, hey, I'm busy doing fintech or Bitcoin mining or artificial intelligence inference training. I want you to go do something. Can you go and move all the data that's at these physical addresses and put it somewhere for me, please? And raise an interrupt so I know when you're done. And that's what DMA engines do. And in Nvme and SDC and so forth, that's typically the way they work. I like those because that means that my processor is now free to do my Bitcoin mining or render my Netflix so I can watch my movie or whatever. And in the meantime, the data is being moved by the DMA. So the way I think of that is kind of like a master and a slave, or a butler and the rich upper class gentleman. So there's a British TV series, Jeeves and Wooster, based on a set of books. And I think of Jeeves as the DMA engine, the one doing all the work, and Wooster is the CPU. Digging into it a little more, I spent quite a bit of time at a company called PMC, which was acquired by Microsemi. I was very involved in some of the flash controller business that we had there. So I'm pretty familiar with the internals of a block device. And I wanted to dig into that a little, just to give everybody a kind of level set on what does a block device look like. And this is a pretty generic diagram of what you might find inside a non-volatile memory solid state drive, basically an SSD, right? So if we look, it's hard to show here, but if we look at I'm going to get down over here. So over here, you can still hear me, I hope. So here's our host processor. We typically need some way of talking to our block device, right? So that could be something like PCIe. It could be DDR even. This could be an Nvme kind of block device. It could be SATA or SAS, right? But it's something that's coming out of the processor. Maybe one day this will be OpenGen CCIX.
which is my name for the mismatch of protocols we have around memory-centric fabrics. Well, we'll see. And then you need a protocol to run on top of that electrical spec. So NVMe has become the standard way for PCIe to talk to drives over PCIe. We didn't always have NVMe. For a while, people were writing their own proprietary stuff and doing their own fancy thing. Fusion IO had their own thing. Somebody else had their own thing. One of the great things that happened quite a few years ago is, a few different standards were working. There was SCSI Express and NVMe, and basically they fought in a room until somebody came out. I think Jim Pappas hit somebody over the head, and we came out with a single kind of common standard. Yeah, see, you're nodding your heads. That's actually what happened, right? And we have a standard over the top. This green box is a chip, like the Microsemi chip, the Flash Tech chip. This doesn't have any memories on it, any storage on it. This is the chip that connects the host to the storage elements, right? And I'll dig into that in a second. It has to talk to the non-volatile memory. Flash is typically talked to using one of two protocols. There's Onfi and there's Toggle. And there's maybe some others, but those are the most popular ones. But this might not be NAND, right? This could be something else. So maybe we're talking to it using something like DDRT, which is a modified DDR with persistence in mind. Maybe it's some other proprietary thing, right? It depends on what the memory vendors come up with. We typically have some DDR to store metadata. In consumer SSDs, we probably wouldn't want to pay for this, so that tends to go away. But in high-performance SSDs, you often have this. And then within the chip, we typically have a bunch of hard-coded stuff that works very quickly, that talks to the host, includes a DMA engine. We typically have some kind of processor, because trying to write RTL for all this and getting it right first time probably isn't going to work. So you're probably going to want to have firmware, and that's probably got to run on some instruction set. This probably isn't a 64-bit ARM with an MMU, but the way SSDs are going, maybe it is, right? In which case, it's Linux, it's full-on MMU Linux capable. I had an interesting conversation in the pub about some of this, but anyway, yeah, very, very interesting where certain things are going. And this will do, run the firmware. You will have some kind of error correction. I used to characterize NAND at PMC, and I would be horrified at how bad that stuff is. I can't believe we store data on SSDs. But we actually use very sophisticated error correction. Andre talked about low-density parity-check codes. That's something that I worked on for quite some time earlier in my career. And they have to run very fast, right? Because this is running in line. So let's say I want to do 1 million IOPS here. That means at least 1 million IOPS has to go through here. And in fact, with write amplification, sometimes you need more than 1 million IOPS through here in order to service 1 million IOPS here, right? So these guys are really big and very important. And then we have some generic interface that converts the bits to the wire. All right? And that's typically what a block device looks like. Certainly a solid state one. So I want to maybe just start shifting gears a little bit and start looking at the latency component of the talk. So this is someone once told me this, and I've always remembered this. Throughput is easy, latency is hard. Okay? I think of throughput as in, how do I get more cars from San Jose to San Francisco? If I want to get more cars per hour between those two different places, I can solve that problem. I can build a bigger highway. I can make it wider, and that means that more cars will be able to go from point A to point B in any given unit time. We have Jeff, I see Jeff over here from Microsemi. We made a lot of money doing that same thing with hard drives. We saw that if you actually striped data across many hard drives, you connected them all together in parallel, you brought them in through an HBA or a RAID card, you could give someone a lot of throughput, using pretty cheap hard drives and parallelism. That's great. Throughput is easy. I'm not going to, it's still work, but it's easy. Latency is hard. Latency is like asking the question, how do I get one specific car, from San Jose to San Francisco faster than any other car has gone before? And that gets hard after a while, right? And eventually it gets impossible because that car is going at the speed of light. Right? You should see how I drive. Right? And unfortunately, and we were talking a little about this at breakfast, but unfortunately, even people like Bezos, with all the money that they have, they are still also bound by the rules of physics. Even they can't move traffic between their data centers faster than the speed of light, as far as I know. Now, maybe they're at the speed of light, but they're not going very faster. I did wonder what would happen if you tried to do it, where you tried to do something and then tried to run away faster, accelerate to the speed of light and then come back. But anyway, my brain started to hurt. But the thing here is throughput is easy and latency is hard. And the hard thing about latency is you don't get to subtract. If you go for latency, you've got to, you have multiple elements of how long your I/O is going to take. Application has to issue it. Kernel has to accept it, has to pass through the virtual file system layer, has to go through the block layer, has to go into the driver, has to get pushed down to the drive has to service it, the drive either raises an interrupt or does something else, and then you basically have to go back, wake up the application. None of those values are negative, because they're all time. You don't get a negative time. I don't get to subtract, I don't get to go, submission queue entry took -1 second, right? It doesn't work that way. So latency always bites you in the ass because it's additive. Quick reminder on persistent memory, even though we're talking about block devices, persistent memory for me has 3 attributes: low latency, memory semantics, i.e. it's not a block device, and storage features, the most important of which is persistence, because persistent memory without persistence is not persistent memory, it's just memory, right? Block devices, low latency block devices, like I'm now going to really start digging into a lot, have 2 of the attributes, but they don't have all 3, right? So we are moving away from the memory semantics here. Like I said, there's good things and bad things about low latency block devices. So why do block? Why don't we just go to the world of persistent memory? Well, I think we've already talked about the fact persistent memory still has some issues that we're working through. It's very exciting. Of course, the other challenge with persistent memory is I don't see a lot of persistent memory in the market that I can go buy today. There is some, and there's more than was a year ago, but we're still, kind of early in our infancy there. On the block system, we can actually do pretty well with block, and I'm going to have some numbers in terms of how fast I can get data off some of these new block devices, and it's actually pretty good. And I want to compare to a couple of other tests that I've done over the last little while. So this table here is interesting. This is basically saying I'm going to do I/O tests on a couple of different block devices. The first one is the crazy, it's not actually a block device at all. It's just basically saying it's storing your data, but it doesn't. This one is actually an NVDIM-N that was formatted to be a block device, so a PMEM0. And this is an NVMe drive. So you can see that the average latency, this NVMe drive is not, I have other drives I'm going to be talking about in a little bit that have much better numbers than this. But just keep this in mind. So for a 512-byte access, you can see, even if I'm using an NVDIM, if I'm looking at it as a block device, I get pretty good latency, but I'm not 100 nanoseconds. Well, I'm talking 512 bytes, so it's not a cache line access, it's multiple. All right. So 3 microseconds here. And a 99th percentile of about 6. My drive is doing 12 and 18. Interestingly, it's better than this one. I suspect there might be a little bit of an experiment error there because, anyway, maybe we'll go back and redo that and do it a little bit. If I ever had a master's student to give me that data, I'd probably slap them, saying, you probably need to run this for longer. But anyway. Yeah. Well, let's keep those numbers in our heads as we go through the rest of the talk. We're talking NVDIM as a block device, 3 microseconds. Let's see how we can do with something else. Right, so I'm a very modest kind of guy. So when I came up with this, I called it the Bates Conjecture. I'm sure somebody else has actually thought of this before, but this is something that I did the other day. I'm sorry the MATLAB here is quite jagged. I'm very happy to put this MATLAB online if anyone's interested and they can see exactly what I did. And you'll actually realize why it's so jagged. But the Bates Conjecture says that if somebody's coming to market with a new non-volatile memory, so if somebody's a memory manufacturer and they're coming to market with it and they're saying, I need to get this into the market, I would argue it will come in as a block device before it comes in as a persistent memory per se. And the reason for that is that the error requirements that we need for this to be a reasonable memory technology are about 1 e to the minus 18, as in 1 time in 10 to the 18 reads or writes, or reads essentially, I'm allowed to have an error on my media. right? That's a pretty big number. That's what we use in the storage industry. This is basically how often can I try to read the data from an SSD and the SSD can't give it to me. But it can tell me it can't give it to me. There's another problem called false correction, where I try to read from the drive and it gives me the data, but the data is not the right data. And that's called false correction, and it has a much lower probability. And there's a man here who knows about error floors and LDPC codes. I spend a lot of time worrying about these problems. So we actually need a very, very reliable media after the error correction, not before. So this is after the error correction. So we know we need 1e to the minus 18 afterwards. Right? With block devices, I get to have very large block sizes for my code words. Right? I'm accessing data in 4K chunks or 512-byte chunks. Those are quite big. So what I posed in my questioning was, assuming the code word size, the error correction code word size is a certain size, what raw bit error rate on the media do I have to hit 1e minus 18? And so what this says is, if you want to read and write your data at single byte levels, the media has to be better than 1e to the minus 10 in terms of its raw error rate. And that's hard. NAND, if you read 1,000 bits of NAND, even fresh NAND, like especially today, now we have TLC, even right at the start of life, there's probably 5 or 6 bits that are wrong, randomly distributed among that 100. Right? In the old days with SLC, it was much better than that, but there's a reason why, you know, I've been kept in a job for a while. NAND is getting crappier, because we don't want to pay for it, right? And the easy way of making cheap NAND is to make it crappy. And that's what we do, right? So it is, right? So basically, as we say, well, let's not address in 1 byte, because I can't make my memory that reliable. Let's address in 2 bytes, or cache lines. Cache lines are 64-bit, right? That's 8 bytes. Maybe 512 bytes, maybe 4K. And what happens is very quickly, the requirement of the raw media goes up. Right? So now the process guys in the lab, the material scientists, are now getting happier, because you're not asking them to build you a memory that works at 1e minus 10, maybe 1e minus 5. They're like, oh, that's actually maybe something we can do. And as we get up here to the kind of sizes that NAND is using, it actually lines up to what NAND is. Well, surprise, surprise, right? So, you know, we're looking at 1 in 100, 1 in 1,000 error rate. It's kind of where the SSDs live. Spin torque MRAM is very reliable. Spin torque MRAM is trying to be down here. Everspin guys will say it's here. My measurements say, yeah. But you know, it's pretty good, right? Spin torque MRAM lives in this world. 3D crosspoint, you know, I honestly don't know exactly what it is, but I'm going to put a serious wager it's in here somewhere. It's not as good as spin torque. It's better than NAND, right? NAND is up here, right? This is information theory. This is like the speed of light. You don't get to break this crap. There's a guy called Claude Shannon. He's awesome. He's not live anymore, but he's awesome. And there's very, very fundamental mathematics about why that curve cannot be violated. Okay? And I call it Bates Conjecture. Do I get to call it the Bates Conjecture, Andrew? So what it means is, if you want to be byte addressable, you need very reliable media. When materials are brought into the market, they typically tend to start crappy, and as the processes are tuned, the yields get better, things get better, right? You can turn the knobs and so forth. So the first materials coming off the line may not be good enough for byte addressability, and maybe it's better to put them in a block interface, put them behind an NVMe front end. Who do we know, which company do we know that came out with a memory that was going to be byte addressable, and now we see it in NVMe drives that may or may not be called Optane? You know, I'm not saying that's the only reason they did it, but it wouldn't surprise me if this is maybe part of the story. The Bates Conjecture.
I have a quick question. Why is the requirement so very different, like 8 orders of magnitude?
Yeah, so it's the mathematics. It's basically large number theory. So the question was, why does it grow so rapidly? And like I said, I can provide, if you like, the MATLAB to do it. It's pretty straightforward. But basically, it's assuming we're using BCH codes with a certain fixed code rate, so I'm not allowed to change the code rate. And I know the output error rate has to be 1e minus 18, which means if you have a small code word size, the chances of having 1 bit wrong in 10 bits is a certain thing. The probability of having 10 bits wrong in 100 bits is much less than 1 bit wrong in 10 bits for the same input error rate. It's kind of like flipping die. So it's kind of tail the curve. I think it's called the large number theory, and it falls out of that. but it's pretty straightforward. And what happens is, as the block size gets big, pretty soon you get to a point of diminishing returns, and you actually saw that, like going from 1 kilobyte to 4 kilobytes doesn't buy you that much, but certainly going from 10 bits to 100 bits buys you a huge amount. Yeah. So let's keep moving. I'm going to be terrible again, aren't I? Oh, God. So low latency block devices are here. They are here. You can go get them. You can talk to my friend Terry here. They have the NV Nitro card. Uses spin torque MRAM to back the data. Microsemi, we had an NVRAM card. It's an Nvme device with DRAM, and it uses a supercap to store the data on power loss. We have Intel's Optane, now to be called Bates Conjecture drives, right? Interestingly, all these devices are NVM Express to the host. Every single one of them. Now, that's interesting. Really, you know, essentially because many reasons we've talked about, the NVMe came along because SCSI wasn't quite doing what we wanted for non-volatile memory. And in the same way, for low latency, SCSI has some issues, and you definitely want to go NVMe. And I think also we're on very much now the path that pretty much anything that's non-volatile memory-based is probably going to be PCIe attached, which means it's NVMe. Right? There are probably a few exceptions to that, but we'll see. They are pretty frickin' fast. So this is some FIO measurements off the NV Nitro card that the Everspin guys were very kind to lend me or let me have. This was FIO, right? This is not SPDK. Am I allowed to swear? I'll get to that in a second. This was in the standard kernel, and we basically just ran FIO testing. And basically, we looked at different block sizes, 512 bytes, sub 5 microseconds. This is pretty fast. This is not too different to the PMEM0 device, remember, 3.5? That's not that bad, right? Here, and you know, here we're not. You know, here we're getting more limited by what's my DMA capabilities. This is the ones that are kind of most interesting. So 5 microseconds. That's pretty good. This is QDEP1, which some people argue is not a very interesting workload, but it is a very good way of testing the response time of the SSD. Also, pretty good quality of service. So this is a different device, but what I did here, and it's a little slower, but what I did here is I did like millions of reads, and then I plotted the probability density function of the reads. So some reads take 7.5 microseconds, some reads take 10. They have some kind of distribution. It looks kind of Gaussian. Large number theory, central limit theory here. Also, lots of math in this talk. Notice, yeah, it's quite tight, right? No I/O less than a certain amount. Certainly no I/O less than 0. That would be an anti-causal SSD. I have a patent on that. I'm going to be very rich. Whoever builds an anti-causal SSD is going to be very rich. And not a lot of I/O out here, right? Hyperscalers, data centers, they hate heavy tails. The whole NVMe this year has all been about how do I, as the owner of an NVMe drive, control what this looks like under my workload patterns. That's it. That's what I/O determinism is. That's what open channel is. The end result, what we're looking for, those that, you know, I/O determinism and open channel are the mechanisms, but the thing we're actually trying to do is have the consumer be able to control what that curve looks like. Whether we can get there or not, I don't know. Another one. This is from an Intel Optane. Same idea. Did lots of I/O. This is, sorry, is in nanoseconds, so divide by 1,000. Honestly, it's not milliseconds. That'd be bad. Again, very tightly bounded, good quality of service. Some pretty funky stuff going on inside that Optane drive. I haven't had time to go work out exactly, but there's something funny. A little bit of a funny little thing. And that was actually, I had a couple of drives and they all did it. So it's like, whoa, I don't know. You're doing something funky in your controller. But anyway. But again, pretty fast and so forth. I'm going to skip through this because I think we're running out of time pretty drastically. How am I doing for time? Anyone?
If she's not holding the sign, you're good.
Yeah, that's a good sign. We'll run through this a little. I was going to step through what an NVMe command looks like. I personally love doing that. I love putting the PCIe analyzer between the host and the drive and looking at what exactly happens. I'm a very sad gentleman. So that's a picture of an NVMe read command, but we'll get into it. Okay, I do have to raise the cat or the dark horse in the room and talk about SPD fucking K. I'm going to actually swear. So this is the name that myself and Sagi came up with when we were very drunk one night, bemoaning user space drivers. So that said, I may, you know, yeah. That said, I think there's good things about it, but I kind of like teasing people, so I keep the fucking in there. So SPDK, for those who don't know, is a user space tool that basically says to the kernel, screw you, do not get involved with this PCIe device. I'm taking it, you can't touch it, you can't manage it, you're not going to look after it and do all the things that sensible operating systems do, like make sure you don't DMA to random locations, etc. I'm going to bind to that memory map region from user space, and I'm going to have a great time. It's going to be awesome. Why would you do that? A, you're insane. B, in theory, well, you know, you are actually bypassing the kernel and the lines of code in there around the virtual file system and so forth. And so that can help reduce latency. Right? Now, we're trying to make the Linux kernel block layer, the fast path, the data path, as low as possible in terms of lines of code. Right? So it's not really fair to say the kernel's got like 10 million lines of code. Those 10 million lines of code don't have to execute for every single I/O. Right? It's, you know, we have ways of streamlining things and so forth. So that's a little unfair. And then the other thing is context switching. So often an application, well, not often, sometimes an application calls via a read command that says, let's read from this drive. Okay? That typically invokes a context switch because we're going through a system call that's a blocking call, and it involves basically flushing TLBs, changing the virtual address map, and whatever. But you don't have to do it that way. We have asynchronous I/O. We have libAIO. You can have a thread that's running and say, hey, do all these I/O, and I'll come and check later on my completion queue to see if it's done. There is, you know, basically in a multi-core system, what happens is another core takes care of the I/O. All right, a kernel running core. Thank you, perfect. So there is no context switch there. The process, the application that's running continues to run, right? It issues the I/O by telling another thread running on another hardware core to go do the I/O, right? So, you know, the context switch thing, I get, yes, but things can be done there, right? The real problem, I think, so to be fair, SPDK, certainly in my measurements, is faster, and quite a bit. So this is the Optane drive. This is the PDF from the FIO testing. This is the PDF with SPDK testing. All right, there's definitely some number of microseconds, and you know, to be honest, you could probably spend months digging into exactly what's going on. Blah blah blah. I didn't do that, but there's definitely some changes there. Right? Interesting. The distribution also looks a little bit different. We'll get into that. And again, I probably should have gathered more data, etc. But I just kind of wanted to make a little bit of a point. The problem is you have taken that block device and you've given it to user space. So anything that's between in the kernel is lost to you. File systems. No. Build your own user space file system. Kernel can't give you one. You're bypassing the kernel. Block trace. Block trace is pretty darn good when things are going freaky, right? It's a lot of debug tools, a lot of capability, a lot of performance analysis tools live there. You lose that. No IO stat. Right? I can't just run IO stat. I can't just run FIO. There is an FIO plugin, but it's a little painful. But I can't just run FIO. I can't run Nvme CLI. Right? Because the Nvme CLI talks to the character devices that are given by the kernel, and they don't exist anymore because you're bypassing the kernel. You can't run Nvme CLI, but it's so good. Yeah, we turn it on. What's that? You've turned it on. Thank you. So you can. But people have to do work to do that, and that work. So, you know, again, we can get in the pub, and you can buy me beer, and we can argue about this. Anyway, so what is, you know, why is that? Why is the kernel not so good? And I'm going to start moving along much faster. I think Martin said it yesterday much better than I did. Martin maintains a section of the storage stack of the Linux kernel, and we have to be we have to be more kind of inclusive. And more conservative in the things that we pull into the upstream kernel. Because we are in all kinds of places as Linux, and we are servicing many, many different people, with many, many different sets of requirements. And making changes that are specific for data center or enterprise is not the way that the Linux upstream effort should go. It has to provide some kind of common value, right? So SPDK doesn't take that approach. SPDK is Intel going, best frickin' networking and storage ever, right? In a server that's probably an Intel server, right? So their requirements are very, very different. Right. But the question then becomes, so what can we do? Okay, and I'm going to really move very quickly now. Polling, we've added polling to the block layer. Martin talked about it a little bit less yesterday. Polling on these kind of devices does definitely help. So one of the drives I had, I was doing 9.1 microseconds with no polling, and then I could get that down to 7.4. That was one of the microsemi devices. It pulls in the quality of service. You pay a price. If you're polling, the CPU that is looking for the completion is going, have you finished it? Have you finished it? This is like my son. Have you finished it? Have you finished it? Have you finished it? Have you finished it? What the? Okay, so we added polling. You can turn it on and have some control on it. We really immediately realized polling from time zero is kind of crazy. It's like, you know, it's like putting, expecting any device to service the I/O in 0 time is crazy. So we thought, well, then let's wait some time to poll. Well, how long should we wait? Well, we started going, well, let's actually measure completion times. So we added some code to measure completion times in the stats, a new stats structure. And we now set polling at half the completion time. So you can basically do no polling at all, minimum CPU utilization, but the longest latency. You can poll all the time, or you can poll half the time. And in this case, polling half the time, we didn't lose a single I/O. In fact, you know, the 7.3 and 7.4 is probably noise in the measurements. So basically, there was absolutely no loss in polling half the time because all the I/Os completed in 3/4 of the time or whatever, right? And that was added in 4.10. We now have the ability, this is kind of interesting. I won't go into the results so much, but it's kind of interesting. We now have the ability that an application can now say on a per iota basis if it's important or not. So we can actually tell, an application can tell the kernel if it would like a certain I/O to be treated with higher priority than another I/O. And that's really just gone in. It's in the kernel for a while. This man here added most of the ties to the system call. The glibc, the libraries, the user space library wrappers that go around the read command and so forth. I don't know, are they in? Like,
so I just know that you brought it up. I thought I saw it on the mailing list, and I'm just doing a git pull in glibc to confirm it.
Thank you very much. They're the joys of open source. Even without it being in glibc, if you know how to write a system call wrapper, it's very easy to get tied into this. But what it means is I can issue a whole bunch of I/O, and I can say this one is important, this one isn't. This one is important, this one isn't. Anyone in the room find that interesting? I would think so, right? You know, these I/O are important.
So this triggers the polling?
What's that?
This triggers the polling?
Well, it tells the kernel it's important. Right now it triggers polling. In the future it may do a different thing. Yeah. Yeah.
Yes, it's in glibc now.
Perfect, great. We also, I'm going to skip this, but we did also realize that rather than just looking at a single I/O size, like averaged over all I/O, we actually want to bin by I/O size. So we're getting more sophisticated there. I'll skip this for the sake of the conversation. You know, there's a lot of people taking a look at this and saying, what else can we add now that we've got all of these things in? What else can we do? And it's open source, so if anybody else has ideas they want to contribute, please come along. It's very easy to get involved. You will occasionally get flamed by Christoph or whatever. But that's all part of the fun. So what's coming next? That distribution curve, those PDFs, the probability density functions, that for me is like what the heck we're spending a lot of time on right now. And getting user space or application space control of that is kind of where we got to go. All right, so how do we let applications send hints or signals down into the kernel around how important certain I/O are, which ones are low latency and which ones are not? So we're starting to do that. We have things like streams, also known as directives, I/O determinism. There's been a lot of talk around that. I/O priority, how do we make sure certain I/O are important? I/O expected lifetime, which is something that Martin talked about. And then we have even more interesting extreme things where we open up the SSDs even more to the outside world, like Open Channel, which I see Matthias is here and I think Laura might be around. Lots of interesting work for that. And the Linux kernel is going to keep evolving. And you know, the last thing I think I'll say is like the Linux kernel has been worked on by some of the best coders in the planet. And I'm not talking about me, I'm talking about the people who are actually doing the real work. And having those people putting in the features that make your storage systems more responsive or better tuned to applications, I mean, you get to benefit from all that work, right? And if you know, and if we will continue to evolve as these devices become more popular and cheaper and higher capacity, and the kernel will allow you to tune for them for your workloads. So I'll stop there just so we have a couple of minutes because I got into so much trouble last time and saved Mark having to beat me.
Good job.
Just a quick thank you to Intel for giving me access to the Optanes, even though I slag off their SPTK.
So who has a question for Stephen? No.
Everyone's in shock.
You finished early so they could ask you
yeah.
questions and then they're not coming through.
There you go.
I got one.
All right.
So if you look at the fit of a memory system, the failures in time of a memory system, it seems like to me that 1E minus 11 is not good enough, especially like for the RAID controllers you worked on, that type of thing.
Yep.
So you just describe why that is good enough?
So the question was around the failure error rate. So 1E minus 18 is the industry standard for an individual drive. So if you put a drive in your system for the drive, for the return error rates. Right? So the 1E minus 11 number was before the error correction, remember? So 1E minus 11 on the media, assuming that there's some kind of Hamming code that's able to fix the errors to get it to 1E minus 18. Now you could redraw that curve, assuming your target error rate is 1E minus 22, if you like, and that'll get you a different curve. It'll have the same kind of shape, but it will be moved to the left or to the right. Yeah.
I think the concern I have is that even 1E minus 18 as a memory system failure rate is not sufficient for many systems.
Yeah, so I think that's a good, like, I would tend to agree with you, Terry. If we are using persistent memory, as in it's storing our stack, it's storing the heap, and it's not a block device, which is kind of storing the storage, it's like not on a file system, then the error rates probably need to be lower again than the numbers I've talked about here. Because now you're not talking about an I/O failure, you're talking about a crash on the stack. And that is a very, very different thing, right?
Any other questions? All right. Oh, one last question, and then we have to be on a break.
Thank you, Aaron.
Wondering if, where do we stand with the gap between SPDK and kernel with this latest low latency work?
Yeah, so I think the gap is still probably around the microsecond mark for the devices that I've looked at. But like I said, I think there is an exercise that needs to be done by, to really dig into exactly what is going on there. And I certainly haven't had time to do it, and maybe other people can comment on what they see. Yeah, so yeah, blatant plug. If you want to learn more about that, you can go to Christoph's talk, which I think is this afternoon.
He's still working on the slides, though. All right, so we've had the anti-Intel keynote, and next up we have the Intel keynote, but after a short break. So please come back at 10:40 for the Intel keynote.
I'm thanking them for their drive. I love you, Intel. I love you. Thanks, Mark.
Damn, is that device slow? The one I have from my slides is way faster.
Yeah. Thank you, Terry.
Great talk.
Thank you.
I sent a picture of you with the
Oh, perfect. Did you send it to me?
I did.
Yeah, please do. Please do. Yeah, thank you.
So our next speaker is Carol Wilder, a Director of Strategic Planning at Intel in the Data Center Group, specializing in storage. In her current role, she leads a team that defines and drives key business and technology innovations for the storage group. Thank you.
Thank you. Well, let me put on this microphone thing. Okay, can everyone hear me?
Test, yeah.
Okay, awesome. So I should say that true to Intel form, if you know Intel, I got reorged 2 days before my sabbatical. And I actually now have system, software, and segments for strategic planning. So storage is part of that, but I actually own parts of AI, the memory subsystems, as well as understanding all of the segments that Intel services. So it's been quite, since I came back from sabbatical, it's been drinking from the fire hose. So that's been pretty interesting. So let's see, let's go on. You now have legally notified. Does everyone feel good about that? So what are the mega trends? Whoops, let's not fall off the stage. I'm going to be down here. I don't know. What's better? Up here? Okay, I'll do it up here. When you look at the mega trends, we look at major things that are pushing storage forward. And when you look at that, cloud, and I want to make sure that it's not just the Super 7. We have a major shift going on between what's going to be on-prem, what's going to be in the cloud, and how to blend all of that data to know where things are and what's the best economics for that. So that's when we talk about cloud economics. Clearly, AI, artificial intelligence. Currently, when you talk to an Intel person, you'll look at AI as machine learning or deep learning. I see it as natural language processing, natural language understanding, text processing, a whole wide range of analytics activities. That's also driving huge amounts of data, particularly, for example, if you know machine learning training. The amount of data that you have to have close to a compute node in order to do that machine learning training is enormous. So that also is stressing out the storage. And then, of course, we have the looming 5G. So we're all looking forward to the Korea Olympics. And 5G is probably going to make its entry there. So you've got all of these things coming together with all of the different devices, with obviously automatic driving and connecting cars, insights for systems so that companies can make decisions faster based on analytics, and then all of a sudden the cloud, with giving a lot more degrees of freedom for businesses to architect what are the best economic price points for their services. We see also this combustion of a traditional economy, so on-prem, storage, scale-up, IT, with the digital economy. So we have a bunch of digital fusion ideas, or a blending of traditional and digital businesses. And when you look at it, smart agriculture, so putting sensors in the ground and knowing what are the plants getting and what's the best optimal conditions to grow crops. We're looking at artificial intelligence, wearables in an industrial sense. You have warehousing, autonomous cars, and then smart retail. I was talking to someone about 6 months ago, and in one store, in one retail store, they only keep one of everything, and they have them RFID tagged so they know exactly where that stock is, and then they can blend it up and know at night what they have to replenish immediately. So they're holding stock in the store in the smallest amount level that they need in order to maximize the profit in that particular store or the series of stores. So we're seeing this bricks and mortar plus AI plus everything else, and what does that think? The data has to be stored somewhere. It's an asset. It's now not just dumping and saying, okay, we have that. It's being used actively all the time. So data is the new oil. I think you've seen that on some of the taglines that Intel has come out with. I personally have a love-hate relationship with that thing. I was telling someone earlier today, it was the name of a report that I heavily contributed to in 2012 to convince Intel to be more of a data company. Well, it's 2017 and we are. So it took about 5 years. Intelligence is the new engine, but storage will be the fuel tank. And we really need to look at, rather than storage being a tax that everyone has to drag along with them, that it's a huge asset. And the intelligence and the insights, and the faster that you can go with that data, then basically you have a much faster virtuous cycle for businesses. But, you know, as with every transformative time which we're in, there are pushes and pulls. So when you look at it, we're looking at performance significantly going up. And we ourselves are driving that with the Optane drives, for example. And I think everybody's seen the press around that. Storage needs and durability. Security. This is one that I think everyone inherently knows has to be dealt with. But how do you deal with this? This is one I just read Diane Green's transcript. She did something at the City Technology Convention, and her first points that she talked about, so Diane Green is head of Google Cloud, I think most people know, but her first thing that she talked about was security. I was very surprised. I would have thought it would have been in their service sector, but the first comment she made was on security. Data throughput and system efficiency. And so these are the things that are going up. We have to be able to maximize for that, but on the same thing, power consumption, latency, reprovisioning time, and then obviously the total cost of ownership. And I think everybody probably in this room has seen total cost of ownership models. They're all different. We've tried at Intel to put those together, and we have these complex things that we have that are run not anymore on Excel spreadsheets. We have them running on some of our databases. And some intelligent systems that we put in place, and we still don't always get it right. And we have a lot of data that comes into those total cost of ownership models, and we're looking at it going, well, wait a minute, we haven't thought about these cases and that cases, and every customer is different. And so when I talk about storage, it took me a while to get everybody in Intel to understand storage isn't about the disk. It's not about the media. Storage is about the strategy of putting compute and data together at the right economic point for that particular service, and then when it's no longer needed to be processed, then moving that storage off to the right economic point for that particular service. And making sure that we have that blend and know what those economic points are and what the technologies that could achieve those economic points are. And this points out this going up and going down. We're seeing this all over the place. Not just in cloud. We're seeing this obviously big time in enterprise. And then there's the whole hybrid cloud. How do I handle that? And we're seeing these requirements change in a big way. But we need to get smarter. We now have all of these data pools, data lakes. And so if we start with the enterprise and we look at that, we still have the traditional scale-up, scale-out models. But moving over, we have orchestration over to the cloud. And how do I orchestrate all of the different resource pooling? What are the right, where the data is? Where does it have to be? But then, Internet of Things, all right? Looking at this and trying to figure out all those consumer devices. What am I going to do with those devices? What do I do with that data? We have the fog, which is that loose connection between what the enterprise is looking at and then all the Internet of Things. How are we going to blend all this together to get one cohesive view? And it's very, very complicated. And the only way to do this is to basically start creating intelligence and start creating self-tuning networks or self-tuning storage networks that basically can read and basically know how to move the data back and forth, or at least let the users or let the administrators know you're not doing the best thing for the economics that you've set. And we need to get smarter. And there's starting to be some examples of this. Clearly, I think a lot of the cloud Super 7 have figured out for their own particular needs how to be able to measure and know and tune their networks, their storage, and their compute in order to be able to get the best out of what they need and be able to communicate the requirements. But those are very specific workloads, very specific markets. I think for the broader generation, or the broader, especially with Internet of Things, I think we're going to have to start to create new paradigms and new use cases and new ways of thinking in order to get that done. So what we see is in this hyper-connected world, which obviously augmenting that with Internet of Things, we have a deluge of data. We've got 5G, which is going to put more and more data on networks, particularly like I've been talking a lot with people, not on automatic driving, but a lot about connected car, which is going to be a huge driver of data centers as we move forward. The data that they need to connect to, they need to collect, but then act upon in order to have a connected car is immense. And 5G will help with that in terms of the latencies between the data center down to a moving car. Cloud processing and analytics, and then all the connected devices. If you have phones, you have watches, you have tablets, you have all of the traditional, and then you have the non-traditional. Echo, Google Home, all of the different smart home devices. And then you have eventually smart cities. So all of that is going to contribute to all the connected devices. We do have a software infrastructure that we started, I'd say, about 3-4 years ago. We've worked closely with SNIA on called Intel Rack Scale Design. And we look at it as there's an orchestration software, and then we slice it up and look at compute pools, storage pools, hot, warm, cold, accelerator pools, and then FPGAs for other than accelerator. And we need to start to think about a revolutionary sort of way to look at all of these different architectures to try to make sense of the world and try to aggregate and know how to help along with particularly storage to get the best economics and the best performance out. Does that make sense? Okay. So just as a plug for rack scale, if you look at traditional server design, all right, you see compute, you'll see storage, and then you see the memory subsystem. So it's generally a fixed configuration with varying degrees of things. When we looked at how we would be able to look at it in a different way, we looked at orchestration layers to do disaggregated, composable resources and pooling as needed. And there's software infrastructure in order to take, and I believe it's open source, that you can take advantage of the compute, the storage, and the accelerator nodes in order to have a better way of managing those for the best economics for the workloads. And then from there, for a workload, you take a slice of essentially what you need for that particular workload. It could be more compute, more storage. It could be more accelerator or more storage with that, and basically look at how to compose it differently in order to meet the needs of workloads and re-provision quickly in order to go look at a certain workload. So this is something that we have been working on for, like I said, 3 or 4 years. It's by no means the perfect answer, but it's a way to look at it that may help in order to maximize profits and efficiency. So when we looked at rack scale manageability, we had to go through several things. Resource discovery, what's available in the node or in the pod that can be used. System composability, how would you compose that for a certain workload? Resource telemetry, so how is it performing? What's the measurements of that performance? And how do we tune that performance to a certain workload? And then obviously manage the resource and the system so that we could make sure that it's optimally performing. So we went from orchestration, we've obviously supported VMware, OpenStack, and then we have custom configurations. We had Pod Manager, which helps with discovery, boot, configuration, and telemetry. And then we have worked on a rack management module, RMM, and then a pooled system management engine. From there, you have all of the hardware resources through some firmware APIs that allow you to hook in compute resources, storage resources, and accelerator resources in order to help with the most flexible architecture for implementation. And all of this software, we provide the reference code, and then it's up to the particular end user to be able to tailor it to what your specific needs are. And we believe that in this way, we're able to, again, like I said before, maximize efficiency and be able to maximize flexibility for customers based upon the economics, the workload, and then any future enhancements that you're looking for. So I wouldn't be Intel unless I talked about hardware. When we look at it, there's 3 slices in the data center group that we commonly refer to. So I'll start with the easy one, which is compute. So obviously, we're a big provider of compute, from scalable processors, so our Xeon FPGAs, accelerators, and then there is a technology, it's called Quick Assist technology. It's basically encryption and compression that is in line for customers. On the comm side, we provide networking fabric, so east to west and north to south connectivity, silicon photonics, Ethernet, and network function virtualization. But in the storage area, we have a number of things that we have announced or that we're working on through open standards. When we look at it, 3D Crosspoint, I think the last, I walked in and the slide said, thank you for Optane on the last slide, which I was like, and I sort of looked, I said, is somebody from Optane here? I didn't know that. But we have Optane. And then we have, obviously, 3D NAND that we're ramping on. SSD and DIMMs, EDSFF, which is the small form factor open, I forget where it's under, but basically it's this idea of having a connector on a backplane, obviously, that has a wider range of bandwidth for future systems that are going to be built. So it can run well up over, I believe, definitely over 32 gigabits per second, but way up over that as well. So it gives the forward-looking flexibility in the latencies that the cloud and others are looking for in that technology. And I know Amber Huffman is driving that group. Nvme, RSD rack scale design storage pooling. And then there is a feature that we have released with the Skylake processors called VMD, Volume Management Device. So with all these advances over the last 2 to 3 years that we've seen coming out of Intel and others, we believe that this coming through allowing storage to be looked at more as a systems level versus as just the disk or just the NAND, All of this plays in for the scalability of storage services at the end user. You can't essentially put in a 3D crosspoint technology, but then use, 10 gigabit, 10 gigabit networking fabrics. That would be a waste. You have this low latency drive with a high latency connect. So you need to scale things based upon what the needs are of the business. And we've invested in each one of these areas to make sure that at the right price point and at the right performance, that we have the right solutions being pulled together. But you can't just have software. You have to have, you can't have just hardware. You have to have software infrastructures that will also scale and provide solutions for customers. Much of what we do open source in order to enable not just Intel, but also some of our key partners. When we look at the, on the compute side, we've recently come out with AVX 512, which has helped enormously in the AI area. And we have that came out with Skylake, and you can read about it online. We've made our FPGA SDKs for OpenCL. We have a math kernel library, MKL, for AI as well. We have a data analytics acceleration library, BigDL. We're working on Neon and deep learning optimized frameworks through our Nirvana acquisition that just happened earlier this year. And we have Cofluent, Studio, and Hyperscan. When we look on the other side in comms, I think there's two that are kind of sisters of one another, or brothers, whichever way, which is the data plane development kit, as well as the software performance development kit, so SPDK and DPDK. These, yes, while they were kicked off by Intel, they are open source and they are not governed by Intel at this point. And we're looking at this as a community activity that everybody can partake in. So if you want to go look at the GitHub for that, feel free. We have many of, in fact, our competitors that use SPDK and DPDK. We have network functional virtualization and single root I/O virtualization in the comm space. And then in the storage space, we're continuing to invest in the ISA-L, which is the Intelligent Storage Acceleration. It's a hardware, it's in the CPU, and we continue to invest and provide that open source as well to the industry. And I've heard nothing but great things. In fact, last year when I spoke at this conference, somebody basically stood up and said, if you're not using that, you're crazy. It's one of the best things. So check it out. Persistent memory over fabrics, we're a huge supporter of that within SNIA. I talked about SPDK. We've got cache acceleration software for storage, and advanced, we spend a lot of time on the AES-NI, so advanced encryption standards and new instructions on every CPU every CPU generation, we invest in that as well. So how can storage be smarter? Last year, I had a very similar slide, if you were here. And we look at the modernization of storage. Clearly, we're seeing right now, it's still largely disks. We know that. But we see this huge, because the economics of SSDs are coming up and the performance is being needed by a lot of services. You see this hard disk drive to solid state transition really happening now. Storage primitives are needed for that. We also have seen the automation and orchestration, so unifying a lot of the cloud and the enterprise storage systems. So more and more, obviously last year I have a huge amount of conversations on how to implement scale-out storage. How do I implement this to gain the best economics and the best flexibility in my storage system? So scale out, hyperconverged, software-defined storage, all of these are things that I think are well known. But as we move over, we're looking at intelligent data management. And this is the extra layer that I think everyone else is really grappling with, is how do you deal with hybrid cloud? What does hybrid cloud mean to you? We see people who are pushing and pulling in and out of the public cloud. I think Nike just announced that they're pulling out of AWS and going back to their own data centers. We've seen Netflix has a bifurcated model. So their customer data is with AWS, but their CDN, their content data network, is with Netflix. So we see this going on all the time. There's this push-pull where the economics for public cloud no longer make sense and they go to a hybrid cloud, or they pull back into their own data centers. What do they need for that? We continue to work with those companies to understand what that data looks like. Machine learning and deep learning. There isn't one customer I don't go visit where they want an AI roadmap. Tell me what your AI roadmap is. And honestly, there's no one AI roadmap. It depends what you're maximizing for AI. Are you maximizing for this very deep training? Are you maximizing for an inference loop? Are you maximizing for just gaining some insights in line? What is it that you're maximizing for? Because that solution for AI looks very, very different based upon the needs for that. Predictive analytics. One of the big things is cars. Think about a car as basically a server on wheels. That's what it is. And that car has a predictive engine at the beginning looking at all the sensors and saying, that's a ball. You can probably run over the ball and you'll be okay. Oh, that's a child. Don't run over the child in a horrible way. But you're looking at that prediction and very quickly in latency having to have the car make a judgment. It's a server on wheels, and they're pumping some data up into the cloud, but the latency from going to the car up to the cloud is not going to be enough to avoid the ball or the child. And so it's basically a server on wheels, and predictive analytics is the engine that basically runs through that. Self-diagnostics. How do I know that this particular pod or this particular server or this particular storage area or storage pooled storage is still operating to its optimal thing? How can I improve that? And then, again, dynamic capacity planning. How do I know that, gee, Christmas is coming? How am I going to change my capacity based upon times of the year, based upon what the needs are of services? And looking at that and doing that. So when you look at the modernization story, automation and orchestration are the foundations, but the intelligent data management and what we build out as an industry for structures and solutions will basically enable a lot of the seamless data services in the data center. And we have to focus on what's that higher level where it's not just about the disk, it's about the system. And it's about removing those bottlenecks that exist in the system so that the data can flow freely at the right economic point for that particular service or that particular end user. And by the way, every industry is different. It's just amazing. I'll go into, and I'm in my Super 7 mode and what their latencies are, and I'll go into another customer and they'll say, oh no, we don't need that latency. We're this, and I'm like, okay, and I'll sit there and I'll go, reset, wipe my mental whiteboard, and I have to redraw the whiteboard in my head again about what their requirements are and covering all those requirements and making sure that we have the right solutions. So we do a lot of support standards. So we have worked with Redfish to address all the data center components with the consistent APIs. In general, and it's funny because I go back and forth with the guy that runs SPDK. I'm always like, okay, well, are there parts of that we think should be proprietary? Is it important? And Nate, who runs it, is always driving against me saying, no, 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 Carol. We need to continue to make this open because we need to continue to work within the open standards and basically enable everybody. And we go back and forth with that. But when I look at this, we do have to have a consistent APIs so that everybody has access to the same information and we have a somewhat of a level playing field in order to make sure that storage and the ultimate end users benefit from the advances that are made. The other is the unified management of servers and storage with Swordfish. Clearly, we've been a huge supporter of NVMe over NVMe Express, NVM Express, and NVMe over Fabrics. It's funny, NVMe over Fabrics, we have done a huge amount of work in specifying solutions for NVMe over Fabrics and looking at what is the best case latencies and shorten those latencies and provide customers with second source opportunities so that they can do the Lego that they want to do. You don't want to be able, we want to make sure that they have options for disks, for Ethernet, and being able to have that storage over NVMe or Fabrics gives them that flexibility for the latency and the needs that they have for that connection for storage. EDSFF, which is the Enterprise Data Center Storage Form Factor Working Group. That down below, if you look, that's what we've affectionately called a ruler, which is the form factor that basically supports, keep me honest, Intel people, I think 1 petabyte, that basically slides into the connector. And we're right now pushing standards for the connector, the backplane, and somewhat of the form factor in order to provide very, very dense storage in a smaller form factor that can be air-cooled. And we're working on that. You tell me.
The petabyte is in a 1U rack of rulers.
Thank you.
Is a petabyte.
Okay, thank you, Jim. I know. So that's the 1U form factor on the picture on the top, right? Yeah, okay, just checking. So we've been working hard on that in order to provide scalability through time and being able to service into 2025, 2030, the latencies and the speeds that are really going to be required from all of the industries, including the cloud. So we've been working hard on that. It isn't finalized yet, but the work is, if you want to join, it's there and it's open. So a call to action. I encourage everybody to try out and look into the new hardware and software technologies. You may not be able or want to adopt any of this now, okay? And the economics for your particular needs may not match with the cost or what's available, but at least it will give you a roadmap of what's possible. Particularly in thinking about this new intelligent data management layer and understanding how to knit that all together for a smarter system. I believe that it's really important to understand what are the tools that could be used. If you have questions, lean back on Intel and on your colleagues, on SNIA, on others in the industry to get better ideas on how to maximize performance and maybe minimize cost and be able to develop new solutions for end users. We have a program that we encourage as Intel Storage Builders, and it's really just, it's a consortium of storage companies, and there's a lot of information that gets exchanged through that Storage Builders program. You just heard Jim, so you can always provide feedback to Jim, and he will take it and help out with that. And then just join us in driving data intelligence end-to-end and fueling the future. And being able to look at storage less about my IOPS or my density or whatever, and looking at it more as a system, and looking at it as what are the bottlenecks that I have to go solve, whether it's networking or whether it's compute or whether it's actual that whole end-to-end story, and how I can make it more intelligent. So I think we have about 3 or 4 minutes, so if there's questions.
Yeah, Brooke has a microphone, so raise your hand and she'll get the microphone to you.
Right there.
Wait.
Wait.
Everybody can hear the question.
Including those online.
Thank you. Thank you for the good presentation. You mentioned that fog computing or fog infrastructure in terms of IoT era. So from storage point of view, how do you think, what kind of features do we need to provide to service them well?
So in fog computing for IoT devices, the way I've been thinking about it, and I think it's far from perfect, is there's little bits of data, okay? Everything has a little bit of data. And the way I've looked at it in the past, and I did a report like, I think it was in 2013 when I was looking at the bits of consumer data. I wasn't looking at industrial, but I was looking at consumer. And I believe that every little bit of data forms a story. And we have to figure out classification systems for the data in order to be able to, with the full knowledge of whoever owns the data, to have a data exchange in order to be able to knit that together and find the overall value. And I believe that's how it has to, in a mind map, look, okay? Then we have to build, if we can get that mind map, then build the storage and the software infrastructure and the hardware infrastructure underneath that in order to support the data exchange model, which I believe is basically how we need to mind map it. But it goes to, and the reason why everyone that I found in 2013 was very reticent to agree to this particular idea, and I think it's gaining much more, is the whole thing about privacy, okay? And what's private data and what's public data. And I think there's a way to knit that together so that it's not, we're not crossing those boundaries as much. And so that's the way I've been thinking about it. And I always go sort of, what's the user really want from this? And then I go down, or what's the business want from it, and go down. And that's where I think it has to move to.
Any specific features that storage needed to provide?
I think it depends on the area. He asked about what are the specific storage needs. Honestly, I think it's going to be huge amounts of storage, okay? Just knowing what I know about, if you think of a car, it's not really an IoT device, but I understand the connected car, and I think this is a similar scale. A huge amount of storage and a huge amount of intelligence on the front end to know exactly what's important and what's not important. And so those algorithms on the front end are going to be very, very important, knowing what you're maximizing for your business. And that's going to be the key. So, but huge, huge storage. And the question, but then I think the other thing, sorry, one more thing. I think what's going to be interesting about it is I think that data is going to go cold very, very quickly, much more quickly than data has ever gone cold, because it's very temporal. And if you're going to resurrect that storage or ever look at that data again, you're going to look at it for additional insights. But that also is a possibility on no-op cycles, on cycles that you have. You might want to go in and look at, okay, what are some significant trends? But you'll be collecting that as it goes forward and basically surfacing it as metadata.
Thank you. Thank you very much. We are
We're up.
now.
Okay.
Thank you.
Thanks, Carol. So our next talk is on persistent memory, new tier or storage replacement. It's co-speakers, Kimberly Keaton and Susan Spence. Kimberly is a distinguished technologist at Hewlett Packard Labs, where her research focuses on data management for memory-driven computer architectures. Her prior research includes storage and information management, NoSQL databases, intelligent storage, and workload characterization. But first, we'll hear from Susan Spence, Senior Research Engineer with Hewlett Packard Enterprise, working on managed data structures software for the machine at Hewlett Packard Labs. Her current research focuses on ease of programming and data sharing for data structures created and used directly in persistent memory. Please welcome.
Thank you. Can everyone hear me okay? Okay. So what we would like to do today is discuss how you might actually use persistent memory. What I would like to do is talk to you about, introduce some of the notion of how persistent memory blurs the boundaries between memory and storage, and then talk a little bit about the context within which we work in this at Hewlett Packard Labs, our memory-driven computing architecture as the context for our work with persistent memory. Now, I know that a number of you have heard a number of talks now about persistent memory, so I'm not going to dwell too much on the technologies itself and the infrastructure. Our intention is to spend most of the time in this talk talking about how you might actually use persistent memory from a software perspective. I'm going to go through a couple of software examples to illustrate this. First, talking about it in the context of using persistent memory as byte addressable memory, and then pass over to my colleague Kim, who will go into some other examples and talk about the challenges for using persistent memory as storage and try and get some dialogue going on that. I've noticed there have been a couple of variations on this graph shown over the last few days. As you're aware, today the technologies tend to fall in this sort of spectrum where at one side you have very low latency technologies but with small capacity, like SRAM and DRAM, and then at the other end of the scale you have these much larger capacity technologies. What we're seeing now is that there are multiple entries. I've actually seen more than two. But to describe just a couple of these, we're seeing, for example, on-package DRAM with massive bandwidth compared to the alternatives at that level of low latency, and then a variety of non-volatile memory or persistent memory technologies in the middle of that space, faster than flash or disk, and approaching the access speeds of DRAM today. So I will note that unlike the SNIA programming group, that Nvme programming group talked earlier in this session, we are using NVMe and persistent memory as interchangeable terms here, so you should not read too much into our use of one or the other in this talk. Okay, quick definition of terms in terms of non-volatile memory. As a number of you are aware, there are a variety of technologies in this space with different characteristics, ranging from NVDIMM-N, where that has very low latency, close to DRAM access speeds, to other types of technologies along the way, ReRAM, phase change memory, etc. And so there are a variety of type characteristics in how you access them and how you use them and what sort of performance you're going to get when you do use them. But the ones that we're particularly interested in are those where you can use byte addressable access to the memory. And not only do we think of it in terms of the non-volatile memory technologies themselves when it comes to actually writing the software to use them, we're also interested in the interconnects to actually get access to this memory. GenZ is one of a number of interconnects that are out there, one that has been promoted by Hewlett Packard Enterprise. There's a consortium with more than 30 companies now involved looking at using the GenZ spec and actually developing reference architectures for this spec. The benefits of this particular protocol, this particular specification, are in particular the ability to globally address very large pools of non-volatile memory, where the fabric that you actually have available to you here, you run the GenZ protocol over, enables you to connect multiple heterogeneous processors, both CPUs and a variety of accelerators can be connected to this fabric, and then they all have access to fabric-attached non-volatile memory on the same fabric. And the ability that, the things that Gen Z provides you are the ability to globally address, for one CPU, for example, or SoC, to actually address any of the memory that is directly attached to this fabric. And this gives you high bandwidth access to the memory and access to very large pools of memory. And it's these types of technologies, both the combination of the persistent memory technologies and the fabric-attached memory capabilities, that enable you to progress from the conventional architectures which are processor-centric over towards ones which are more memory-driven centric architectures. So for us, when we talk about this in Hewlett-Packard Enterprise, when we think about what it means to be working in a memory-driven computing context, we're interested in the fast persistent memory available to us, the fast memory fabric, task-specific processing, and then the opportunities for new and adapted software to take full advantage of these capabilities. It's that last one that we want to focus on today. HP has made significant progress in the memory-driven computing space. Announced this year the world's largest single memory computer with 160 terabytes of fabric-attached memory using this type of memory-driven architecture. And 40 physical nodes, and in particular, using optical interconnects. We have an X1 photonics module that enables us to access this memory very efficiently and over very high bandwidth interconnects. So this gives us significant advantages that we want to take advantage of when it comes to actually programming this. So when we put it together, what we actually want to do is converge memory and storage. That's what we're looking at here. Being able to say what happens from, what are the implications for what are the implications for software if we actually move to a byte addressable persistent memory model, replacing hard drives and SSDs. What happens when we actually have this resource disaggregation, where we have this very high capacity, large pool of shared memory, all attached directly to this memory fabric? How can we take full advantage of that? One of the advantages of this type of fabric-attached memory is we use topologies that enable us to have very near uniform, low latency access to all of the pool of memory from any of the SoCs or other processing components that are attached to that fabric. And this gives us a very low latency, high performance tier as a result. Oh, sorry, that's actually referring to the volatile memory. Okay, so then the question is, how does the software take advantage of that? We have the ability to deliver memory speed persistence. We have the ability to have direct access over this fabric to these large pools of memory. But it should be noted that for this type of architecture that we're talking about, this is non-coherent accesses between compute nodes. And we also need to consider the implications of that. So if you consider memory-driven computing in this context, this means that conventionally we have worked either in a shared nothing architecture, as shown on the left, where you have SoCs each with their own DRAM and their own non-volatile memory technology, and they are sharing nothing with, in principle, with SoCs on the other parts of the network. Or we have a shared everything architecture, where we have a coherent interconnect, ensuring that we can use these in a coherent, all of the DRAM and or NVM in a coherent way across the whole fabric. But when we actually move to the architecture that we're working in now, we're looking at something that we call a shared something architecture, where each of the SoCs has its local DRAM, but any of the SoCs can access any of this shared large pool of non-volatile memory across the fabric. So the questions driving the memory-driven computing software work that we've been doing in Hewlett-Packard Labs include: how do I use persistent memory? How do I take full advantage of byte-addressable persistent memory? How do I share data safely in a large, globally addressable pool of memory? and in particular ensure data consistency in the face of failures and errors. This is clearly important to customers using it. And as we get larger, this pool of memory gets larger, how do we scale effectively to make real good use of this large memory, many core systems? We tend to look at the software to address these technologies in terms of three different vectors here. First, we consider that memory is large and how to address that, how best to take advantage of that. We also consider memory is persistent and memory is shared non-coherently over this fabric. And there are opportunities in all these spaces. For example, where memory is large, we can have very large in-memory data structures tailored with the implementations tailored specifically for these very large memory systems. And we can create very large indexes to reduce storage access taking full advantage of this large memory. Where memory is shared over the fabric, we have the ability to move from a model where, in order for different storage nodes to process over the same data, they no longer have to copy that data in one phase of operation from one SoC to another node to operate over the same data in the next phase of operation. They just simply pass a reference to the shared data in this shared pool of memory. This enables you also to do things like have multiple processors communicate through the memory. One writes to the shared memory, another one reads from it. And it enables easier load balancing. No longer do you actually have to copy data in order to reassign work from one processor to another. You simply pass a reference to where the data is, and the other processor can take over the work that was previously done by an overloaded processor and more load balance the work more easily and much more quickly across these multiple nodes in the system. And where memory is persistent, opportunities include no storage overheads if you're working with things in memory that also happens to be persistent memory, fast snapshots, fast checkpointing. These are some of the things we've been able to demonstrate with the software that we've developed for persistent memory. And that means that we've been able to develop a memory-driven computing developer toolkit to explore all these different areas. We have a number of different software that some of them fall into the intersection. So we have some software addressing large memory, some large persistent memory, some large shared memory, and a variety of these. And all these bits of software we've developed and made available open source as this toolkit to enable other people to see how we have explored the challenges and opportunities of using large memory, shared memory, persistent memory, and what APIs we're using to take advantage of persistent and fabric-attached memory. So let me talk about a couple of examples of the software that we have developed and made available open source through this toolkit to give you some examples of how we use it. The first example here is a write-ahead logging library. We see persistent memory as a natural fit for improving database workloads. And we've explored a number of different opportunities in this space for improving database performance, database throughput, by using persistent memory, and particularly byte-addressable persistent memory in this space. So for write-ahead logging, we are particularly focusing on the aspects of the fact that the logging is really your bottleneck when it comes to database throughput. And if you can lower the latency to get those log entries to persistent state, you increase the throughput of your system. The persistency, latency is critical to your transaction performance. So I'm sure many of you are familiar with write-ahead logging in principle. The key things here are ensuring all the modifications associated with a transaction are written to the log, and ensuring that those changes are persisted in the write-ahead log to a persistent state. Traditionally, that's been done by writing to flash or disk. What we've been doing is experimenting with how to take full advantage of non-volatile memory technologies, particularly NVDIMM in this case, to enable low latency logging. So one of the things that we've done is we've been using the technology from our ProLiant persistent memory servers. They're battery-backed NVDIMMs, which enable you to write to persistent memory with DRAM access speeds, but ensuring persistence of the data that is written to those NVDIMMs. So this gives us the best performance, the lowest latency for data access and for data writes. And it's backed by NAND flash, which ensures persistent storage for the NVDIMMs. Now, in the initial experiments we did it with a very limited capacity to start with, just using a simple 8 GB NVDIMM to actually see what advantage we could take, even if we have just a very small amount of persistent memory to play with. And we find that what we could do is write the log entries, the tail of the log, to the NVDIMM. It does require us to truncate the log because we don't have a lot of space to play with on that 8 GB NVDIMM, and therefore we have to checkpoint the database, that type of thing. But it does give very good results. It enables us to store the tail of the log in the NVDIMM, and then in the background destage the log to the disk for capacity. The application doesn't have to worry about the details of doing that destaging. It's all taken care of in the write-ahead logging library for persistent memory. So they don't have to deal with the application logic involved there. And it does significantly improve performance for a MySQL benchmark that we tried. Now, having said that we worked there with an 8 GB NVDIMM, I would like to point out that on the persistent memory servers that ProLiant is selling today, the Gen 9 ones, there is actually up to 128 gigabytes of battery-backed NVDIMMs on those servers today. And with the scalable persistent memory servers that are coming in Gen 10, second half of this year, this goes up to 1 terabyte of persistent memory available that you'll be able to buy and use this year for persistent memory. So as we head up to 1 terabyte of persistent memory available to us, then there are many whole databases that you could actually accommodate in persistent memory, not just the log or the tail of the log. And we want to think more generally about how you can actually take full advantage of these persistent memory technologies, and particularly byte-addressable persistent memory technologies, using these types of approaches, using approaches that take full advantage. Consider, for example, that a traditional database system has multiple software layers, each with their own format of the same data. So your application is working with data structures. That's what your programmer really wants to work with. So they make changes in their data structures. Those data structures then, typically if you're working in Java, for example, then get translated from your Java data structure representation to some relational representation for the database, then get pushed through the client, through the server. The relational database table representation in memory gets written to pages, gets written out through the buffer cache, and ultimately ends up in sectors on flash or disk. So then the question is, well, you have a lot of different data formats for the same data that you have to maintain at different layers of your software. That's a lot of overhead in a variety of different dimensions that you have to maintain. What if you just had a single layer of software, your application, plus a runtime library linked directly into your application that enables you to create and use data structures directly in persistent memory, have those data structures persist your data as in this single representation rather than having the multiple different representations in the different software layers. This enables your programmers to develop software much more quickly, maintain that software if you need to change things much more easily. It enables a significant ease of programming and makes the overall work required and resources required from your system much less than in the multi-layer system. To explore the benefits and advantages and benefits of this, myself and a couple of my colleagues have, for the last 4 years, have been working on a library called Managed Data Structures to explore and provide an example of how this might work in practice. And the two key benefits of this type of approach, where you're just working with a library linked directly into your application, means that you can have significant ease of programming. Application programmers create data structures, lists, maps, graphs, whatever they may be, directly in persistent memory by calling the MDS APIs to say, create me a managed data structure directly in persistent memory, and I will read and write through your APIs to this data structure directly in persistent memory. We provide APIs in multiple programming languages as a proof of concept that we can in both managed and unmanaged languages, Java and C++ here. And the programmer simply accesses those data structures through references to the data, makes direct reads and writes, and then has the ability, once they have those data structures in memory, to be able to share those data structures with other processes that use them. Remember, we have a large shared pool of non-volatile memory to play with. In order for one data structure to share that data with another, they simply pass a reference to the data structure in persistent memory for another process to be able to use at the same time. And our library provides the appropriate high-level concurrency control mechanisms to ensure that this data sharing can be done safely and ensuring consistent data in the face of multiple processes using this data at the same time. Kim, would you like to go through the next examples? Okay. All right. Yes.
Right, so can people hear me if I talk into the microphone here? People are sort of. Okay, maybe we actually do need to.
These are not working as well as lavalier. I can give you this too.
Let's try this for now. How about now? Whoopsie. Probably turned it off.
There you go.
Now? Is that better? Okay, awesome. All right, so the examples that Susan has gone through really focus on our how we exploit persistent and really large memory, and those two aspects of that Venn diagram that we saw earlier. I'd like to shift the focus now and explore what we could actually do with fabric-attached memory as well. And so the work that we've been doing in this space really is using a key value store to perform this investigation. You might ask, can I just use a traditional scale-out key value store architecture and just run it on top of the fabric-attached memory? Sure, you could certainly do that, but it won't allow you to take full advantage of the sharing that's possible with this fabric-attached memory. So let's just consider what this architecture is. A conventional key value store basically uses a shared nothing approach, and the idea is to divide up the key space amongst the different nodes that are in the cluster. So each node is responsible for just a part of the key space. And the idea is that clients are going to ultimately try and contact a particular node for the particular request that they care about. They may actually hash the key to determine what the appropriate node is themselves, as they do in Redis. Or they may actually send a message to any of the nodes in the system, which can then proxy to the appropriate node. But so ultimately, though, the request is routed to the correct server, and then that server handles the request. That works well, but there's a potential shortcoming if you have very skewed access patterns. If some keys are much more popular than others, then there's the potential for there to be a lot of load imbalance between the different servers here, because some servers are serving up popular keys, others are serving up less popular keys, and so as a result, there's really not an easy opportunity to balance the load between them if we go with this strict partitioning of the keys between the different nodes. So we can't really share we can't leverage the shared pool of non-volatile memory in order to do better load balancing in these skewed access pattern cases. So the work that we're doing and have done is to really explore what would it mean to do a shared something key value store. And the idea in that architecture is essentially to store the data in this fabric-attached memory in such a way that all of the nodes can have access to it. So any node could conceivably serve up a request for any of the different key and value pairs. And so we'll see how this actually works in the next couple of slides. The high-level architecture, there's really kind of two main pieces of this that we've worked on and have open sourced. And so the bottom part is the memory management and how do we allow those nodes to share access to the same memory. And then the top part is really a set of indexes that we've used to implement the key value store functionality, to store the key value pairs and to be able to look up things. And so our goal here is to be able to allow all of the different nodes to have access to the same data sets and to be able to serve up requests. Any node can service any request. And the way that we're going to do that is to use the fabric-attached memory as well as the memory semantic primitives, so things like atomic operations, in order to allow us to provide concurrency control, fault tolerance, as well as load balancing between the different nodes. And in particular, I want to highlight some of the work that we've done on some of the memory management components as well as the indexing components. the way that we think about memory management in the machine program that this work comes out of is really as a kind of a two-level memory allocation and management scheme. And so at the kind of the base level of things, we want to be able to allocate chunks of memory. So think about this. We're talking about 160 terabytes of fabric-attached memory in the prototype that we built that Susan mentioned. So we want to be able to start by allocating very coarse granularity kind of blocks to the nodes to be able to share. And then from there, we can have a second level of memory management that will actually provide finer grained access in a way that is tailored to the applications that want to use it. So at that coarser level is what's illustrated here. And so the metaphor that we've been using is of a library and a librarian who is the entity that's responsible for making all the good decisions about how to allocate and share memory. And the allocation units are in terms of what we call books. So it's an 8 gigabyte chunk. And you can actually group together multiple books into a shelf. And the shelf is the entity that's going to then be exposed by the librarian to the rest of the nodes that are running applications. And so the way that we've chosen to expose this to those applications is through a file API. And so we're calling that the librarian file system. That's a little bit confusing for folks that associate other things with LFS, but work with me here for a moment. And so this librarian file system is then used to expose these shelves. A shelf has a name, you can mmap it, and then be able to use that either to build a file system on top of or to have an application framework, such as the managed data structures framework running on top of it, or in our case, we can run a key value store on top of it. So this is the basic level, sort of that coarse-grained allocation. The next level of allocation that we've been looking at is that finer-grained allocation. And we've layered what we call a non-volatile memory manager on top of that. And so the goal here is to provide that finer-grained allocation than what the librarian file system provides. And it also is responsible for allowing sharing between the different processes running on potentially different nodes in the system. And it's also for tolerating the failures of those processes and the compute nodes that they're running on. And so the idea is that the non-volatile memory manager will allow us to allocate free and named shelves, these multiples of 8 gigabytes. And then it will also provide a global addressing scheme. So I want to be able to address a portion of this fabric-attached memory. There's this notion of a shelf ID plus an offset within the shelf. And that's a global pointer that will make sense no matter what node that things are operating on. And just then, if I've mmapped that, I need to be able to translate that into the virtual address that's being used on the particular node in question. And so there are two different APIs that we've provided here. One is just to expose those shelves directly through a region API for mmapping purposes. And the key value store uses that for its own internal bookkeeping. But then there's a second API, a heap allocator, that we're using so that applications can actually do regular alloc and free calls. And so that can be much smaller granularity for data structure manipulation and so on. And the nice thing about this is that the heap allows us to have an allocation that happens on one node, but then a free operation that can happen on a completely different node. And the memory manager is actually able to take advantage or understand what's going on and also then be able to support that access across multiple different nodes in the system. And this is a general library that can be actually used directly with other applications. We've happened to use it in the context of our key value store, but this has been independently open sourced. Now on top of that, we're building indexes. And so for a key value store, you might think, well, the obvious data structure here is a hash table because that allows me to do a get or a put of a single key operation. And so we would like to give ourselves the option of eventually having the ability to do range lookups as well. So we've started looking at ordered indexes. The most popular ordered index that you might think of would be a B-tree that's used commonly in relational databases. A challenge with working with B-trees in the context of persistent memory is just that when you add something or remove something from the B-tree, that might have a knock-on effect. You might then have to dramatically change the structure of the underlying B-tree and the intermediate nodes of that B-tree. And so as a result, it becomes more challenging to do that in an all-or-nothing atomic fashion. So instead, there's some interesting work that the community is really recognizing that radix trees, or compacted prefix tries, are actually another alternative that provide ordered indexes, but that have much better properties for operating on top of non-volatile memory. And in fact, there was a paper earlier this year in FAST from some of the folks at UNIST that looked at a right optimal radix tree for looking at non-volatile memory. So we're going to apply it here in the context of fabric-attached non-volatile memory. And so the basic idea is that, as you can see, there are, so this is the list of things that is represented in this radix tree is shown on the left there. And so we have Romain, Romanus, and all these words that are hard to pronounce, I guess, and Ruber. And so the idea is that we look for the shared prefixes, and then we can actually compact those and only store the kind of the common prefixes as to what the intermediate nodes of our tree look like. And so the idea is that if we want to be able to add something or remove something, we can do that with a combination of operations where we can basically do copy on write kinds of operations, and then with an atomic operation, atomically then install those updates into the radix tree, so that the new material that goes from not being visible to being visible in a single instruction. So let's just look at an example of how that would work. So if we wanted to add the word radix to this particular radix tree, we would allocate the space for the value, 0, as well as the leaf node that has the unique suffix associated with radix. And then in that single atomic operation, we could actually add the pointer that would install it into the rest of the tree. And so as a result, these radix trees are more amenable to fabric-attached non-volatile memory than B trees would be, because they have this more localized kind of update pattern that allows us to take advantage of these atomic operations. And again, this is a library that we've also open sourced as part of the work that we've been doing. So this is just scratching the surface of some of the work that we've done, what Susan and I have described. There are a number of other pieces of software libraries that we're also making available to the community, and some of those are shown here. I know this is a busy slide, but let me just try and walk you through some of the aspects of it. So on the bottom right-hand side, we have a series of emulation and simulation tools. So you can actually inject delays if you want to emulate fabric-attached, or if you want to emulate persistent memory of a variety of different speeds. We also have the ability to do fabric-attached memory emulation by having a virtual machine that acts as a node, and then you have a shared set of actual physical memory underneath that plays the role of the fabric-attached memory. So both of those emulation tools are available. We also have the librarian and the librarian file system, as well as some other modifications that we've made to Linux to allow Linux to operate in a world of fabric-attached memory in a non-coherent processing kind of an environment. So those are extensions to the PMEM-IO libraries to handle the non-coherence, as well as libraries to handle the fabric-attached memory atomic operations. And then finally, in the data management and programming framework space, we've talked about some of these projects, but we also have other non-volatile memory programming kinds of favorite frameworks, things like Atlas, as well as NV threads, as well as checkpointing libraries, and modifications to Spark to make it run in a large memory environment. So lots of good stuff there. And then finally, at the application level, we've got a couple of application examples looking at image search as well as large-scale graph inference. So that's a whirlwind tour through some of the examples of the work that we've been doing and open sourcing. Let's switch gears for a moment and think about this question of, is persistent memory memory or is it storage? So let's see a show of hands. How many people think it's memory? Okay, yeah, we've got a fair number of people. How many people think it's storage? How many people think it's both? Yeah, all right, I'm with you on that. So when someone asked us this question earlier this week, we basically said yes, it's both of those things, depending on how you look at it. So we've spent a lot of time talking about how persistent memory looks like memory and how we can treat it like memory. Because we have the ability to avoid layers of software, we can pass references back and forth and whatnot. But if we want it to have the properties of storage, if persistent memory is going to be the new storage, then it has to actually safely remember persistent data. And there may be a little bit more work to be done in order to make sure that that can be true. So if persistent data should be stored basically reliably in the face of failures, it should be stored securely in the face of various exploits. It should be stored in a cost-effective manner, as Carolyn was mentioning earlier. And then it should also be using a data access API that makes sense for the underlying device that we're looking at. And so let's just explore some of these ideas in a bit more detail. If we think about, would you entrust your persistent data to some of these new memory technologies? Well, if you're going to do that, you need to be able to deal with the fact that non-volatile memory may not always work. There may be endurance issues. Like any device, it may fail. We also need to deal with the fact that the actual devices themselves could be stolen, or there could be software exploits that would actually violate the security of the data that's being stored there. So there are lots of challenges that still need to be addressed. The good news is that the storage community has spent decades thinking about these issues, right? So there are lots of techniques that we can draw on for thinking about replication, erasure coding, encryption, compression, deduplication, and so on, wear leveling. And so the challenge really here is how do I apply these ideas in the context where we're operating at orders of magnitude faster speeds than we are with traditional storage devices. So it's memory speed, not storage speed. So these traditional solutions also are going to complicate some of the benefits that we see from the new direct access technologies. So think about if you've encrypted something or compressed something in memory, now that's going to kind of get in your way of being able to directly access it without doing some amount of decryption or decompression. And so there's also a question about space efficiency and how can I do that how can I store redundancy in a space efficient fashion given that these technologies are going to be perhaps more expensive than other parts of the memory hierarchy. So lots of different potential solutions here. One would be that we could just go and implement all of these ideas in software, the way that we've done sometimes in the context of storage today. That's certainly an option, but it's going to mask some of the benefits of the new technologies, as you can imagine. And so as a result, we are expecting that there'll be more combination of hardware and software kinds of techniques that are being used here. So for example, we may want to employ hardware acceleration for certain kinds of common operations. So things like DMA-style data movement between different parts of the system, or being able to zero memory or copy things, and potentially be able to do encryption or compression, or even redundancy schemes. So an open question for the community is really what are the kinds of functions that are ripe for this type of hardware acceleration? And so that's something for us to all talk about together. In addition, we can think about wear leveling in the context of non-volatile memory. And so there are lots of discussions about what's the life cycle of these kinds of new technologies. And so repeated accesses may certainly exacerbate the wear issues, especially if I'm trying to coordinate through memory. So then there's potentially some additional uses for memory in the process. So what's the right balance between having some flavor of hardware-based assisted wear leveling versus relying on our application software or middleware to actually do that for us? And then finally, if we want to understand what's going on in our memory system, what's the equivalent of SMART for non-volatile memory systems that will allow us to be able to give the telemetry and to be able to report what's going on in a way that we actually can understand what has happened, what will happen, and so on. Another question is, load, store, accessible memory is not necessarily going to be the most cost-effective form of storage for forever data, data that's potentially very cold and not going to be accessed very often. And so, echoing some of the things that I heard Carol say this morning, we need to find the right storage tier for the right type of data accesses. So you could imagine that now we've got different types of technologies that are best matched to the particular kind of access that we're looking at. So, we may choose to put scratch or ephemeral data in the faster storage, use our persistent memory to store, temporary results or results that I'm actively accessing, and then finally, store things more durably or in an archival fashion on slower storage technologies. So how do we actually manage this memory hierarchy so that we can ensure that the data is in the right tier when we need it to be? And then a final question is really around what's the appropriate API for the technology? And so we've talked a lot about memory and load store access to persistent memory technologies, and that's a really great thing, but that's going to work well to a point. If the memory latencies are in the hundreds of nanoseconds and lower, that'll be great. But then as we start creeping up higher, the load to use latency for all of the different things that we're trying to do here, might be too long for processors to really want to wait around for in a synchronous fashion. So then we start to think about more I/O-like interfaces, read or write or get put, that would make sense for those longer latencies. And you'll notice that there's definitely a gray area in there, in the couple of hundred nanoseconds to low number of microseconds, where for some applications it might still make sense to do load store access. For others, maybe it doesn't, depending on what the synchronicity and sharing patterns are. All right, so just wrapping up, those are some of the ideas that that we have for persistent memory as memory versus storage, and some of the open questions that we need to be able to address in order to really truly persist data in these new technologies. If you're interested in learning more about some of the work that we've been doing in the memory-driven computing space, there's certainly a lot of things that are published on our machine page. We also have a machine user group that is allowing people to have dialogues with one another, dialogues with the folks that are working on these projects, and then the memory-driven computing developer toolkit is also some of the product of that machine user group. Finally, we're also on social media. So to wrap up, as we've seen, persistent memory is blurring the line between storage and memory. New technologies like Gen Z memory, semantic fabrics, and whatnot, the combination of these different things are really allowing us to rethink programming models and rethink how we want to think about data management, to simplify the software stack, to enable us to focus on memory format persistent data. And it really allows us to rethink things all the way up the stack, from the low level, sort of operating system kinds of things, all the way up through the application. We have some initial ideas and some initial forays into that space that we've shared, but we think that there are many more opportunities for innovation. And so we'd encourage you to think about how would you exploit memory-driven computing. So with that, I'll pause and see if there are any questions.
We're out of time for questions and encroaching on lunch, but please see Kim or Susan in the hall to ask some questions afterwards. Thank you very much. So a little bit of logistics for lunch. We have two setups, and you'll notice that we open the far one first. That's to get everybody out of this little bottleneck right here. So please go to the far lunch first, and then fill in the last one. We also have winners of the $100 gift certificates. The first winner is John Bush from Jack Henry and Associates. And the Tuesday survey winner is Domingo Rios from Embraer, Brazil. So get those surveys in, answer those questions in your app, and we'll see you after lunch.